Okay, maybe while we're getting started on setup, I'd like to introduce myself. I'm Tobias Kippenberg. I work at EPFL, and I work in the field of, or I lead the laboratory of photonics and quantum measurements. And part of our research is interested in studying the coupling of light and mechanical motion. And another part of my research is interested in generating optical frequency combs using optical microresonators, a field called microresonator frequency combs. And within CLEO, I've been giving a short course on optomechanics, and this field is now pretty well established. It started maybe like to really take off about 10 years ago. And what I'd like to do in the short course is give you an overview of optomechanics, emphasizing more the fundamentals. In the second part, reviewing some of the more modern developments. Good. Thank you, everyone. Perfect. Okay. Okay, so now we should also be fine with the screen here, and okay, good. So I hope that your resolution is fine with everybody. It looks like we had a little bit of an issue earlier today setting it up. So then what I'd like to do today is, as described, tell you about the field of optomechanics, and really what I have in mind, kind of for this short course, is the following. What I'd like you to appreciate and like to is that the coupling of light and mechanical motion is a canonical system that's used in optical interferometry, and that has, as I'll describe in the second part, a variety of kind of applications. One thing I'd like to focus on this course today is in particular of something that is, especially in the first part, I'd like to focus on how you measure mechanical motion using optical interferometers, how you can quantify the sensitivity, and also what I'd like to outline is the fundamental limit on sensitivity called the standard quantum limit. And so that's really what I'd like to do in the first part, talk about quantum limits of displacement sensing. And the second part, what I'd like to spend time on, is show you how radiation pressure can be used to cool mechanical motion, amplify it, and also tell you about applications of mechanical oscillators. Okay. And so let me get started. So the kind of tutorial is set up in the following way. So I said I'd like to first describe the basics of optomechanical coupling, describe how you can obtain very sensitive displacement measurements, how you can use radiation pressure to cool, amplify mechanical motion, and talk about this so-called standard quantum limit. And as I described, the tutorial is kind of set in two parts. Now, one thing I should mention, there are some slides which actually in this version are not marked, but they're supplementary slides I put in that I will not discuss in detail here in this course. But if you're interested to find out more about a certain topic, I've tried to give more detail than maybe can be covered in this course. Another aspect that I've done is each slide contains references, and those are, on the one hand, not complete, but on the other hand, those are those references that I personally find actually very helpful and useful. So I put kind of a collection of reference in there for different types of topics. Okay, so maybe let's get started. So optomechanics has to do with the coupling of light and mechanical motion, and one should realize is that mechanical oscillators are really ubiquitous in science and technology. And I'll give you a few examples of mechanical oscillator as used in science and technology. One example is tuning forks that you have in typical watches. Accelerometers, mechanical oscillators are also used in cell phones. For instance, a modern GSM kind of cell phone, what it has is a so-called F-bar resonator. And these are piezo-mechanical resonators that are used to create filters. And one of the prime reasons that you use mechanical oscillators in filtering or timing has to do with the fact that mechanical oscillators can have high quality factor at room temperature. Okay? So if you were to make the same kind of megahertz oscillator, not from a mechanical device, but rather from a discrete device of inductances and capacitances, so LC circuits, then what you would find is that an LC circuit has typically an order of magnitude, or many orders of magnitude lower quality factor. And that's the primary reason you use mechanical oscillators for filtering or timing. It's just the Q at room temperature can be very high. An electrical Q of a circuit will not achieve the same kind of value. And of course, mechanical oscillators can also be used for very sensitive measurements. An example is the atomic force microscope. You can even be so sensitive that one can detect even the presence of single spins with such an AFM. If you functionalize the cantilever with magnetic tip, an island, and so on, all these examples the mechanical oscillator is used as a transducer or as an elemental filter. And today, what often is used is a so-called quality factor frequency product as a figure of merit, and that's typically bounded by about 10 to the 16. So the typical upper bound for QF product at room temperature for a mechanical oscillator. Now, mechanical oscillators are more of a quantum objects. Okay, you can quantize mechanical oscillators. Okay, and just like any harmonic oscillator, you can do so. So they have a Ladder spacing of h bar omega. They have a well-defined, ground state. And if you ask, okay, what temperature does it take to move a mechanical oscillator into its quantum ground state, that would be for 1 megahertz oscillator, you would need a temperature of 50 microkelvin. So these are very, very low temperatures, and it's not something you can readily generate with a refrigerator. And one way to achieve such low temperatures is in fact using the interaction of radiation pressure with the mechanical oscillator to cool the mechanical oscillators to these low temperatures. And I'll describe you experiments actually that have been carried out over the last decade that take mechanical oscillators and can place them into their quantum ground state. Now, to gain control of mechanical oscillators, what you ideally like to do, especially if you're interested in exploring mechanical oscillators in a quantum regime, is you like to first of all reduce their thermal occupancy. So this is the number of thermal quanta. And say for 1 megahertz oscillator at room temperature, you would typically have millions of quanta. So it's a very highly kind of classical thermal state that you have. At the same time, you also like to have a readout that's very sensitive. How sensitive? A typical scale, a natural scale of comparison, is the so-called zero-point motion. So if you this half energy or half quanta of energy in the quantum ground state, you can convert that into equivalent displacement fluctuation. And say for a nanomechanical beam of say of typical kind of nanograms of mass, the zero-point fluctuation would typically be on a scale of 10 to the minus 60 meters. So these are very small kind of displacements. And also like to have very efficient readout. And so these kind of aspects can be accomplished with cavity optomechanics because you can, on the one hand, make very sensitive interferometric position measurements at the level of the zero-point motion and even below. You can also achieve very efficient coupling to the light field, also strong coupling. And you can also take these high thermal mechanical occupancy and cool mechanical oscillators to the quantum ground state. Now, so maybe starting out with radiation pressure as a means to control mechanical oscillators, one should review some of the early work done in that field. And really one of the pioneers in the field of radiation pressure was, in this case, Art Ashkin at Bell Labs. And already in the 70s, he was developing methods by which you can trap particles in laser fields. And you typically distinguish two forces. One is a scattering force. So if you have a laser and particles or light is reflected, you have 2 h bar k momentum transfer, and this is typically called scattering force. But there's a second force. That's the force also Art Ashkin was looking here at, and it's a gradient force. And the gradient force is a force that's transversal to the Poynting vector, so it's a transverse force, which makes a particle being moved to the center of, for instance, a focused laser beam. And these techniques of optical trapping are still used today in the field of biophysics, for instance, to study the motion of molecular motors. So, and earlier even, or in the 16th century, was pointed out by Ducometes that radiation pressure must exist as observed by looking at the comet tail during transits around the sun. So, as I described, kind of these ideas of trapping and cooling can even be taken to a further level. And in fact, already 5 years later, 1975, Hensch and Scharlau, Demuth, and Weiland proposed a method by which you can use radiation pressure to cool a mechanical oscillator. And so what I've put here, in fact, is the original kind of paper. So it was literally more than a conference abstract. So I think it's kind of a record in terms of citations per word. But in that little article, they outlined correctly the idea of sideband cooling, how you can sideband cool an ion that's trapped in a penning trap, and you can you shine light that's detuned with respect to atomic transition, exactly by omega m, the harmonic trapping frequency, and you can cool that way ions to their motional ground state. And this was achieved in ions already a long time ago, already in '89. And what's interesting is that this trapped ion ground state cooling not only opened the opportunity to look at, for instance, quantum computing with trapped ions, where these motional degrees of freedom play a very important role, but also they're used to make very precise atomic clocks. So the most precise atomic clocks today, for instance, at NIST in a group of Dave Weiland, they use the motional degree of freedom and the ability to cool that to the ground state as as a way to perform kind of actually logic on the ion transitions. And so the question is, can you also use radiation pressure to cool mechanical oscillators? And that has been really a central theme in this field of optomechanics over the last 10 years or so. And so if you go back, then in fact, there's a kind of saying that for every invention or discovery made in the Western world, there's at least one Russian who thought about it before. And that's been the case for atomic laser cooling. And so if you look in literature, what you find a paper that was published in 1969. So it's already before Art Ashkin, before the laser cooling from Hensch and Demuth in Wineland. And this was the investigation of dissipative polymotive effects of electromagnetic radiation. And so what was meant here? So what Brzezinski was considering is the effect of radiation pressure, which he called here polymotive effect. And he was considering the effect on a mechanical element rather than an atom or ion. And he was realizing that this can be used to actually cool it. And he called this a dissipative effect. So it's an effect where you are actually removing energy from a system. And his experiment looked the following way. So he had a microwave cavity. So this is just, in this case, a long tube where microwaves are propagating back and forth. And they're reflected off this end vane here. So this end vane is mechanically compliant, so it can rotate. And so as the vane is moving, it changes the path length of the cavity, so you have what we call a parametric coupling. And what he was considering and realizing is that the microwave radiation pressure could actually make that end mirror lose energy. You could actually cool it. And this he called this polymotive effect. Okay, so it's not a cooling of individual atoms or ion, but rather of mechanical oscillators. And so Brzezinski's kind of central question was, yeah, what's the influence of radiation pressure? Yes?
I'm referring with the meaning about the radiation pressure, not just the radiation. What's the difference between radiation and radiation pressure?
The radiation pressure is just the forces exerted by light, right? And there's different terminologies we'll find in literature. People call it radiation pressure. You also find the distinction of the scattering force versus gradient force, depending on which direction the force acts. What you also find is this effect of polymotive. Polymotive is also the force acted by light. And so it's all synonyms for radiation pressure. And so radiation pressure is a very faint force. If you have kind of 1 watt of power, and you shine it off an object, that gives you a 6 nanonewton kind of force. Okay, that explains why you would never notice the radiation pressure from the sun. And again, it's very simple to calculate. Every photon has 2 h bar k momentum transfer. You multiply it by the flux, and there you go. It's just 2p over c is your radiation pressure. And so why was Brzezinski considering this radiation pressure in first place? And the reason he was considering is that he was in the 60s already interested in gravitational wave detection. So very, very early on, he had the idea of using these interferometers of microwaves to detect tiny little length changes of test masses, and in particular use those test masses as probes for gravity waves. So this was a very, very kind of forward-looking kind of experiment, and it took more than 30 years, almost 40, right, to actually get gravitational wave detectors to work. And they don't use microwave radiation, but rather optical radiation. Okay? But the principle is precisely this. It's a parametric transducer. You have an optical kind of mirror. It's coupled to the optical cavity field A, and you have some input and some output fields. And I'll give a little bit of a description of the input-output coupling. So, so again, in the case of gravitational wave detection, let me just mention the mechanical mirrors that are described here are just the pendulum modes of a mass on a fiber spring. And so and typically you have a relation between displacement x and the force you apply to the mirror, and it's given by the mechanical susceptibility. And so you might wonder actually why, for instance, in these gravitational wave detection experiments, do you place the mirrors actually on this very high Q suspensions? And this becomes very obvious if you plot this susceptibility as a function of frequency. What you find is that the ratio between the off-resonant response and the peak response, that goes like the mechanical quality factor. So if you have a very, very high Q suspension, all your thermal energy sits in this very kind of narrow peak, and if you go away from resonance, you have this nice kind of off-resonant noise floor where you can do experiments. And that's the reason why you suspend, for instance, AFM tables or also these mirrors on high Q suspensions. So high Q suspension gives you very low kind of thermal noise floor away from resonance. So it's maybe not at first sight intuitive. So, so what was Baginski considering? He was considering to use these cavities as interferometers. Okay, and the principle is very simple, and that is the following: your cavity, if you send in light and you have a light that comes out, then you have obviously the intracavity field that follows the Lorentzian shape. So if you're on resonance, you get an enhancement of the intracavity field by the so-called cavity finesse. So that's the cavity buildup factor. Okay, and if you were to move this mirror, then you will move off the resonance of the cavity. And if you look at the phase response, for instance, of the light that gets reflected, then if the cavity is overcoupled meaning that the losses of the cavity are dominated by output coupling losses, not internal losses of the cavity, you have a pi phase shift across resonance. So if you sit exactly on resonance, okay, and you modulate the mechanical oscillator position, you transduce a small displacement delta x into delta phi. And the proportionality constant is just a finesse of the wavelength. And so what you can see here is that if you have an optical laser field with a short wavelength and a high optical finesse, you can make that transduction very efficient. So a very small displacement gets transduced into a corresponding large phase shift. Yes?
Okay, so if we move the right side of the cavity and then going to change the resonance, what is going to change if we move the right side of the cavity?
If you go to the right side of the cavity?
Yeah, move the right side of the cavity over there.
Yeah, you can also, sorry, if you put your laser here on the side of the line. Yeah, I'll talk about that. If you move the side of the line, for instance, here, then your signal of the mechanical motion is not transduced to the phase fluctuation, to the phase quadrature, but rather to the amplitude quadrature. And so it's not a way you can actually detect the motion. But for simplicity, I've just shown here an example where you probe on resonance. And so did it answer the question? Or,
Yeah.
Okay. Well, I'll talk in the later part of this tutorial is what actually happens if you exactly when you bias your laser here on this side of the resonance, because that leads to amplification also of cooling of the mechanical oscillator. So, so just some very kind of basics of optomechanical coupling. So first, how would you describe mathematically such a system? And in principle, it's a very, very simple set of equations. So the first is your cavity has some resonance frequency omega naught. And so if you now have a mirror that's mechanically compliant, okay, you just have here a we call frequency pole parameter G times X. It's a position. What is this G for a microresonator? Well, it has to be omega over L, where omega is the cavity resonance frequency and L is just its length. So the shorter you make that cavity, okay, the more efficient you transduce any kind of displacement change into a change of the phase. Now, what you can also do is you can now construct like the full equations of motion, and many actually papers in optomechanics they use what's called the Lungman equations. And so you might ask yourself, okay, what's the equation of motion for the intracavity field that's being driven by an external input field? And in principle, it's a very simple set of equations. So the intracavity field A kind of, first of all, decays with the cavity decay rate, kappa over 2. Okay, why is it 2 here? Because energy decays with kappa. The field decays with just half that rate, so that's why it's there at 2 here. This is the field decay rate. Then you have the detuning of the cavity, delta, and this detuning now is dependent on this displacement gx. Okay, so this frequency-induced displacement by this optomechanical coupling, and you have an input term. Okay, and so what we often find is that this input term is just written as root kappa external times s, and s squared is normalized to power, a squared is normalized to energy. That's why there's a square root of kappa appearing here. Okay, and this kind of a very widely kind of adopted kind of nomenclature to describe the input and output fields of a cavity. And so what you can do with this input-output formalism, you can solve the equation of motion. Okay, for instance, for the amplitude response of a cavity and the phase response, and this you do by just moving to Fourier domain and making use of one very handy relation that I'll just flush here once, because you send light into a cavity and you have light coming out of the cavity. And you might ask yourself, how are these related? And that's a relationship that was worked out by Gallina and Collet many years ago. It's called the input-output relation. And it tells you that if you take the output field, that's the same as the input field minus then the square root of kappa x times a. Okay, it's a very handy relation if you ever want to calculate the transmission response of a cavity. Okay, that's single-sided, double-sided. That's typical. That's your kind of a very handy, important relation. So on resonance, then obviously, say if you have a Weismann-Garrity type of cavity, you drop all the power inside the cavity. We call that critical coupling. That's when your external coupling rate is equal to the loss rate. And then you also have this characteristic phase change across resonance, and that depends actually if on the ratio of losses inside the cavity versus outside versus outcoupling losses. So only if the cavity is fully overcoupled, okay, you actually get this pi phase shift. Otherwise, actually that phase shift is less. Okay, so so how can you now describe also the mechanical oscillator? So again, the cavity field is simply given by this very simple equation. You have the detuning of the laser to the cavity, here encoded as delta. You have this optomechanical coupling Gx. You have the decay of the field due to dissipation. A portion of the dissipation comes to output coupling. A portion can be internal loss. And then you have this external drive that drives the cavity. So this describes the optical cavity field. How would the equation look like for the mechanical oscillator? And that's very simple. So the mechanical oscillator is just a harmonic oscillator. It has some damping rate, okay, 1 over tau. It has some eigenfrequency omega m. And then you drive it kind of by radiation pressure force. Okay, now how does that radiation pressure force look like? That radiation pressure force, okay, is nothing else than the number of photons in the cavity. So here a squared of h bar omega, that's the number of photons in the cavity. And now if you think about it, each photon, when it travels once around the cavity, in say a circular Whisper gallery cavity, it transfers 2h bar k momentum. Okay, if you now also divide here by the round trip time, then actually you get the photon force, and that force, okay, is exerted on the mechanical oscillator. So this is all the equations that encapsulates optomechanics. So it's extremely simple. Okay, so it's just an optical field coupled to a mechanical oscillator. Yes?
So how does, for example, the noise for the laser, for example, amplitude and phase noise, influence these equations? Is it just an additive term?
Yeah. I'll actually show how it works. But what you do is, so these are typical equations for the means, for the mean fields.
Okay.
And in reality, what you have to do is, if this is the input field S, S can be, say, the mean input field, but in reality it has a fluctuation, plus delta S, for instance. And that delta S could then be your amplitude noise. If you want to describe phase noise, actually it's a little less trivial, because phase noise actually sits, the way you can best describe it is by adding another input. If S, say, is your field, and let's assume for the moment it's real, then amplitude noise would be plus delta S, but delta S is also real, and phase noise would be I, say delta Q, and where I is now the square root of -1, and that sits exactly in the orthogonal quadrature. So then you can also kind of describe how phase noise actually gets transduced into the system. And actually, I'll show some equations that go through that. But in principle, so these equations that couple now the optical field to the mechanical oscillator coordinate, these are classical equations. Okay, they're not quantized yet, but they describe the core kind of optomechanical physics. And so from this, you can, for instance, derive the way you can read out mechanical motion. You can derive, for instance, what we call the spring effect, how you can cool or amplify motion. What you cannot get from these equations is there's no quantum mechanics inside here. Okay, so there's no quantum noise entering, no classical noise entering. These are just purely equations for the mean fields. Yeah. And so how can you solve these equations? Well, first of all, you notice that these are nonlinear equations because you have a squared here. So inherently, radiation pressure is a nonlinear process. It's a three-wave mixing process, and because you have a squared here. Now, one thing I should mention is that these two equations give rise to, again, how do they give rise to this physics of Brzezinski that I alluded to earlier? Well, let's take a look at this first equation here of the mechanical oscillator. So we've written here in a slightly different form with a damping rate gamma m. So this equation is nothing else than a damped harmonic oscillator that's with eigenfrequency omega m that's driven by radiation pressure. And so to understand, in a nutshell, okay, this effect that Brzezinski was considering already in the 60s, this amplification and cooling, all you need to do is you go to this equation of the mechanical oscillator and you ask yourself, okay, what happens if you were to displace the mirror very quickly? Okay, so you have this cavity here and you displace quickly the mirror. What happens then? Well, intuitively, what you understand is that the cavity has some finesse, it has some quality factor. So the photons will take some time, okay, till they have equilibrated to their new equilibrium position. And that's just the ring up time of the cavity, or ring down time of the cavity. So what you can do is, heuristically, you can say this mechanical oscillator is driven by radiation pressure, but that's not instantaneous in the position of the mirror, but rather it's this little delay here, tau. And this delay encaptures the fact that whenever you displace the mechanical oscillator, it takes some time for the field to adjust to that new equilibrium position. So if you write like this, what you can do is just Taylor expand the right-hand side. And if you do Taylor expansion, you get two terms. One is a term that's proportional to x, and one is proportional to the x dt. So the first term, this is actually an optically induced rigidity. So the mechanical oscillator spring constant is stiffened or weakened, okay, depending on that sign, and it adds to the intrinsic omega m here of the mechanical oscillator. The second term, that's viscous, that's velocity dependent, and it can have two signs, okay, and this sign of the f dx depends if the laser is red or blue detuned. So if the laser is red detuned, what happens is that the damping, okay, is added onto the damping of the mechanical oscillator. It's actually, the damping is increased. It leads to cooling. Or if you have blue detuning, it leads to an amplification. The damping is negative, and then you generate what people call a phonon laser, okay, a coherent amplification of the phonons. And so this is precisely the calculation Brzezinski did in his original book, already back in the 60s. And it is this effect that he was describing, because it's cooling if you have this negative detuning of the laser. Now, this term also has, or the way this is now formulated in literature is that you call this effect dynamical backaction. So why do you call it backaction? So backaction is describing a process by which you're trying to make a measurement. Okay, in this case, a measurement of the mechanical oscillator position. The radiation pressure has an effect, you know, that acts back on a test mass. And in this case, it's dynamical because it invokes this delay, and that leads to an amplification or cooling. Okay, and this effect is also of practical relevance. Okay, not so much the cooling, but rather the amplification. Because if you amplify mechanical motion, that means that at some point you will undergo an instability, you will undergo kind of a lasing transition. In this moment, the mirror starts to regeneratively oscillate, and that limits practically, for instance, how much power you can place into LIGO. And so, in fact, LIGO is worried about this effect for a right reason, and because LIGO has observed this dynamical backaction amplification about 2 years ago by injecting too much power in the interferometer. And so, so Brzezinski, as said, he conceived very early on this idea of using the coupling of light and mechanical motion to make very precise measurements. And he predicted already in 1969 two aspects. One is that you can amplify or cool mechanical motion. He called this effect parametric instability because it's something you want to avoid when you run an optical interferometer. And these interferometers, as we know, they exist now. They've been built. It was one of the most successful kind of scientific endeavors kind of in the history of physics experiments. This is an example of the Hanford and a laser interferometer gravitation wave detector, and observatory, as it's called, LIGO. And it consists here of these 4 kilogram test masses, separated by 4 kilometers, arranged here in this orthogonal fashion to detect gravitation waves, which are tidal waves, so which shorten kind of the space between two mirrors in one arm, lengthen in the other. And what really is happening in this experiment is actually quite interesting. You're really depositing energy of the gravitational wave in the mirror. So the mirror actually is literally damping this gravitational wave on a scale, of course, that's absolutely minute. But that minute amount of energy that's deposited in the mirror, that's what actually LIGO detects. And so the sensitivity for this experiment in terms of strain is 10 to the minus 22. So that this is kind of so these are mind-boggling kind of sensitivities that are needed. Okay, so it may be quite obvious and natural that in these LIGO interferometers, this idea of parametric instability, so driving the mechanical mirror motion, is still a very faint kind of effect. And the reason it's faint is that these mirrors are 4 kilogram heavy, and the typical powers that you inject in a LIGO interferometer are on the orders of hundreds of watts. So circulating powers are kilowatt scale, but these are still not sufficient, okay, except in this one instance I described, to observe this parametric instability. But what's now another comment is that this idea of detecting with optical interferometers a gravitation wave has an even earlier version, which is not using an optical interferometer, but rather a so-called Weber bar. And there you have, again, a test mass. It's coupled to an LC circuit. And what's done here is that this test mass is changing the capacitance, okay, of your circuit here. So you have a mechanically compliant capacitance. And then the entire resonance frequency will depend on the position here of the test mass. So this also is a parametric coupling, okay, except now that you couple the mechanical oscillator to an LC resonance, okay, via this parametrically varying capacitance. So maybe one comment, you can also ask yourself, is there a more fundamental description of this coupling of light and mechanical motion? And what I've described is there's two equations, one for the optics, one for the mechanics. But in reality, okay, of course, you can describe the system at a much more fundamental level. Okay, any optical interferometer that has a mechanical oscillator coupled to a light field, you can describe by Hamiltonian. Yeah? And this is simply telling you what the energy of the system is. And once you have a Hamiltonian, you can immediately find the equations of motion just by applying your kind of standard, Heisenberg equations of motion to the different fields that you have. So how does it look like for a mechanical oscillator coupled to radiation pressure? So I'll just very formally show it. So you have A dagger A, that's number of quanta in the optical field. B dagger B is number of quanta in a mechanical oscillator. Now you can ask yourself, what would be the coupling between light and mechanical motion? And the way you can find out that coupling is very easy. The classical radiation pressure force is nothing else than the flux of photons times 2h bar k. Okay, and that's equal, if you reformulate it here, that's equal to the number of photons in the cavity. So the mean number of photons times h bar g. So h bar g is the per photon force. And now that's a classical quantity. How can you make it quantized? Well, you actually replace n here just by the number operator for number of photons. So this is the radiation pressure force, okay? A dagger A times h bar g. Now that's the force. What's the energy? Well, force times displacement. So you multiply that by x, and that's your Hamiltonian, okay? And so this is just the radiation pressure Hamiltonian. And if you look at it, so this was first worked out by Law, Casey Law, in the 80s. It's a three-wave mixing Hamiltonian. So if you're familiar with nonlinear optics, right? This is an operator you would encounter, for instance, in a Chi2 crystal. Okay, you have three fields interacting. So here, two of the fields are optical, one is mechanical. So it's a three-wave mixing. Okay, and if you want to be more formal, what you can do is you can express x. This is just your operator for displacement. So it's a 0-point fluctuation, b plus b dagger. And then you have your radiation pressure interaction, which just tells you that your mechanical oscillator, b plus b dagger, so this is the mechanical oscillator position, is coupled to the optical field. And then you have this interesting kind of product of g times 0-point motion. Now, this actually has a very physical meaning. So g, what I mentioned, is how much you shift the cavity by displacing the mirror. If you multiply this by the 0-point motion, okay, that tells you what is the frequency shift of the cavity due to the vacuum fluctuations of the mechanics. Yeah? And normally you would think this must be an extremely tiny kind of number. So how much would a cavity, what's the vacuum fluctuation of a cavity of a mirror? How much can that possibly shift the optical resonance frequency? And what's very interesting is in an optonanomechanical system, this number can be absolutely gigantic. So there's now the largest numbers in the field are about 10 megahertz. So the vacuum fluctuations of the mechanics shifts you by 10 megahertz of actual frequency. So that means that you really are starting to see, okay, any kind of motion in the mechanical oscillator. Okay, certainly thermal motion, but even down to the vacuum level. And this number here, this product, is typically called G naught. Okay, that's a vacuum, the vacuum coupling strength. So, so this is this number here. So G naught, this vacuum coupling strength, is the frequency pole parameter times 0-point motion, and that's how you parameterize the strength of the interaction. Now, when you have this Hamiltonian, what's nice about the Hamiltonian is you can immediately recover your equations of motion. Okay, in a rigorous fashion, you can calculate what the optical frequency shift is. So you apply kind of Heisenberg equations of motion to A. You apply Heisenberg equation of motion for the momentum of the mechanical oscillator, and then you recover your conventional kind of coupled mode equations. Now, if you look carefully, what you find is you don't recover everything. Okay, these equations do not include losses. Okay, so those you have to put in. There's a rigorous way to do this, but one either you can put them in by hand, okay, or you go with what people call the quantum Lundgren equation, okay, where you allow then also the fields to decay and interact with the environment. So now, I said the first part is more formal. Then we'll look at some more physics. But let me still make a few more comments about this interaction. So this radiation pressure interaction goes like A dagger A times X. So it's a three-wave mixing. It's a nonlinear kind of process. But in many cases, and this is certainly the case for most of the kind of process in nonlinear optics, there's typically one strong drive field, right? So what you typically do, and which is permissible, you can say this operator A, really what it is, it's a classical driving field, A bar, and then you have some vacuum fluctuations, delta A, okay? And if you plug this in for A dagger and A, okay, you can linearize. And what you do is you just keep terms that are proportional to A bar. Okay? And for instance, products of delta A dagger, you neglect. Yeah? And if you do that, then your Hamiltonian gets much simpler. Okay, your Hamiltonian then takes a very simple form. You have, and this is shown in one example, if you excite with a laser, detuned by omega m, okay, so what we call the lower sideband, then in fact you get a just beam splitter type of Hamiltonian. And what this does is it annihilates a quanta in a mechanical oscillator, so delta B removes a quanta from the mechanics. It creates a sideband on the optics, delta A dagger, or it does the reverse process. It, for instance, in this case, it creates an excitation in the mechanical oscillator and removes one in the optical field. Okay, so these are very kind of simple kind of Hamiltonians, and the coupling strength now between light and mechanical motion is just given by how many photons you have inside the cavity. Now, even though these are, in principle, this is a quantum description, let me mention is this description is perfectly valid also for the classical fields. So if you can take the average of the equation, you recover the normal classical equations of motion, and if you're interested how noise is transduced through a system, you would also use this as a starting point. So these are the equations of motion now for the optics and the mechanics. And again, now I've written it here not in terms of A and in terms of X, but rather in terms of delta A and B. Okay, B is the mechanical oscillator here. You get coupled mode equations, and these you can solve. Yeah? How would you solve these? Well, you would just go from time domain to Fourier domain, and then these are algebraic equations that you can, for instance, solve in Mathematica, and here they are. So what are the solutions? So here's the interesting aspect. If you solve this system, okay, you can calculate this so-called mechanical susceptibility. And this mechanical susceptibility I mentioned earlier, it contains the resonance frequency of the mechanical oscillator, its damping rate, okay, and also the mass. Okay? But now what happens is, due to this coupling to the optical field, this susceptibility here gets modified. And first of all, what you can see is that there's not just the intrinsic damping gamma m, but there's this optically induced damping gamma opt. And this is the radiation pressure damping that you add. And this can either be positive or negative. And how does the damping look like? Well, if you look at the equation here, it's simply actually two Laurentian that you subtract from each other. Actually a minus here, not a plus. And when you subtract these two Laurentians, okay, this is just a, you can make this density of state asymmetry positive or negative. That actually causes damping of the mechanical mode. Also, what you see is that the eigenfrequency, gamma effective here, is also changed. And this leads to an optically induced kind of damping rate, spring constant. So what happens here is that the mechanical oscillators, of eigenfrequency can shift either up or down due to this radiation pressure interaction. Okay, so there's a very simple kind of way to understand now the kind of physics of radiation pressure. So for instance, if this is your density of states, this is the mechanical oscillator here, say at megahertz frequency, this is the optical cavity. Then if the laser is detuned by omega m from the cavity, what happens is that photons that enter the cavity can only do so if they remove omega m of energy. So that they need to bridge that frequency difference by removing a quanta of mechanical energy from the oscillator. So this is a cooling process. On the other hand, you can also have an amplification process. So when you detune a laser to the upper sideband, then photons entering the cavity can only do so by also generating a phonon, and you actually are amplifying the mechanical mode. Yeah? And so again, in the quantum mechanical language, what people would call these processes is they would call the process of cooling, they would call this a beam splitter type of interaction. Okay, so you have always this B delta A dagger and Hermitian conjugate process. Okay, they would call the amplification process a parametric down converter or two-mode squeezing. Okay, and it's also very intuitive. Why? Because if you are in the upper sideband here and you generate a photon in the cavity and also the phonon, okay, it's a two-particle creation process. You create always one photon and one phonon. That's why people call this kind of a two-mode, two-mode squeezing process. In fact, it's the same Hamiltonian for optical parametric down conversion. And if you're on resonance, then you have both. Okay, you have both kind of processes that look like the two-mode squeezing, and you have processes that look like cooling. And if you actually pump a resonator very strongly on resonance, what you will generate is squeezed light. Okay? And the reason you generate squeezed light is because of this combination of processes that you have here. So what I'd like to mention and go through is some experiments that now embody this optomechanical interaction. And what I do here is I show some of the work that I'm most familiar with, which is the work for my group. Okay? And so I want to give you some example of how this radiation pressure coupling can be observed and witnessed and lead to experimentally observable kind of phenomena in optical resonators. And so now I'm not going to talk about macroscopic resonators, but rather optical microresonators. And here's one example. These are so-called Whitspern-Gary mode microresonators. This is one made in glass, but you can make them from many other materials. They even exist fully chip integrated. And these devices, they confine light for long amounts of time in now masses that are nanogram, not kilogram, like in the case of LIGO. But what's interesting is that these devices are also mechanical oscillators. So just like a wine glass has a mechanical mode of a few kilohertz, kind of these devices have also a radial breathing mode of a few tens of megahertz. And this anti-radiation pressure physics that Braginski outlined in the 60s, you can observe also in these micro and nanomechanical structures. Except now that the masses are so small that these very faint radiation pressure forces are much more kind of easily observable. Yes?
So what happens, for example, if you modulate your laser beam? How is this transferred into the mechanical motion?
Yeah, so you would, so what happened in that case is you would, if that modulation is resonant with the mechanical oscillator, the mechanical oscillator modes, in this case the radial breathing modes, would actually start to be excited. So you can drive actually mechanical motion also directly by modulating a laser beam. But the type of driving I'll describe here actually is a different one. Here, the driving is what we call autoparametric. If you just detune the laser, okay, it will generate the modulation of the laser beam itself by the cavity dynamics. So the external lasers can be just continuous wave. So if you have a continuous wave laser and you detune it with respect to resonance, you can amplify or cool mechanical motion without applying any kind of modulation. Because the modulation of the laser actually is generated by this coupling of light and mechanical motion. Any motion of the mechanics imprints back on the optics and generates actually a modulation that's resonant with the eigenfrequency. And so, so in this case with these toroid resonators, there's a mechanical breathing mode that has a frequency about, in this case, about 50 megahertz. It's coupled to the laser field. And you can ask now the question, what is this G naught? Okay, what is this vacuum coupling rate? And for this structure here, so say for a Whitspern-Gary resonator with maybe a diameter of 30, 40 micron, that coupling rate is about a few kilohertz. Okay, so you might argue, well, that's actually very small. But if you think about it, if you have a CW laser that you buy from NKT Photonics, those can have a line width, short-term line width of less than a kilohertz. So these are pretty sizable couplings that you have in these structures. So optomechanical systems exist in a variety of forms. As I described, the first idea of optomechanics really emerged from LIGO, and over the last 10 years, there's many, many other systems that consist of photonic crystal, Whitspern-Gary mode resonators, membranes put into cavities, but they all kind of share the same kind of Hamiltonian. It's this radiation pressure Hamiltonian that couples light to the mechanical motion in a linear, or as you call it, parametric way. Okay. So what's the rough scale of the eigenfrequency? So if you have a structure and you ask yourself, okay, what's the mechanical frequency going to look like? Well, it's a very simple kind of calculation. You just take the typical radius or characteristic length scale of the resonator. Okay, you divide it by the speed of sound. Take the inverse times 2 pi. That's actually a good estimate of the mechanical eigenfrequency. And so, for instance, for Whitspern-Gary mode resonators, those lie anywhere. These are tens of micron in diameter. Kind of those frequencies typically lie. The fundamental frequencies lie in the range of 10 to 100 megahertz for these type of structures. If you go to photonic crystal, okay, beam, for instance, that has say a diameter of half a micron, those frequencies will be vastly higher. They will be typically about 5 gigahertz. So, what forces do you have in dielectric cavities? Well, it turns out that it's a little more richer than one may anticipate at first. And there's, of course, the canonical kind of radiation pressure force that comes with momentum transfer, so the scattering force. Photons traveling around have a 2 h bar k momentum transfer. But there's 2 other forces that exist. And one of the forces is called electrostiction. So if you have light actually traveling down a fiber, okay, what happens is that the light actually will exert a force onto the fiber itself that tries to pull, okay, the molecules of glass to the center. And this is very similar to this gradient force I mentioned from Art Ashkin. Okay, another similar experiment that you can think of is if you have a capacitor and you have a dielectric, the capacitor gets sucked into the dielectric. It's often there's the same kind of force. So it's called electrostriction. And this electrostriction is in fiber response for Brouillon scattering, okay, or for guided acoustic wave scattering. And also in Whitspern-Gary resonators can give a contribution to radiation pressure coupling. Except now that the sign of this electrostriction and radiation pressure, they don't have to be the same. In fact, they can even be opposite. They can even cancel each other. And this is an effect that's in particular relevant for photonic crystals. And then there's the gradient force. If you have, for instance, two dielectrics spaced closely to each other, you get a bonding anti-bonding mode, and that gives also a corresponding force. That's then called the gradient force. Now, as I described, there's many systems where this radiation pressure coupling exists, and in some where it's very non-trivial to see actually the actual kind of contributions of the different individual effects. This is an example from Oscar Painter's group at Caltech where they looked at photonic crystals. And what's done in the upper part here is, in both cases, these are COMSOL simulations, so fine element simulations. You can also do them with other programs like ANSYS. Actually, ANSYS is really the industry standard. COMSOL is more used in the academic environment. Both are finite element solvers. So in the upper graph here, the entire structure was solved for Maxwell's equations, okay? And in the lower part for the Poisson equation. Okay, and what you see in one case are just the eigenmodes of the optical eigenfrequencies of the photonic crystal. And there's a defect, that's why you have different, the fundamental defect mode, the higher order mode. And here now you have the mechanical modes. And the mechanical modes here in this case are kind of pinched modes and also accordion type of modes. And you can see that these are co-localized. Now, if you want to calculate what the coupling is between the two, what you effectively have to do is you have to do a perturbation theory. And you have to ask yourself the following question: if you take one of these mechanical mode patterns, how does it shift my cavity eigenfrequency? And it's highly non-trivial to see for the case of photonic crystal how that coupling is manifested. And that's what you have to do is you have to really evaluate, okay, by using the strain field of the mechanics and the optical field, how much frequency shift you have. Now, one subtle aspect in these photonic crystals is that you have to take into account this strain optical coupling. And that can actually be very sizable. So it's not just sufficient to calculate the contribution for moving boundaries, but you have to also take into account, the increase or decrease of refractive index due to strain in the material. Now, if you do that, and these devices, you really get coupling rates that are on the order of megahertz. So 1 megahertz of coupling rate due to the vacuum fluctuation of the mechanics can be imposed on the optics. So that's actually bad news for those of us that are trying to make narrow line with lasers, because if your vacuum fluctuation, or it gives you 1 megahertz of frequency shift, right, then at room temperature you'll have very, very large fluctuations. So it's never a good idea to make a laser, okay, that's very narrow line with a very small cavity. So this is certainly telling you why that will fundamentally not work. You can also do near field coupling. You can bring a resonator into the close vicinity of the optical field. The same situation happens as you bring the resonator into near field. You have an added dielectric. You get a redshift of the resonance. Okay, that redshift changes with frequency, and the derivative gives you the kind of the coupling rate. So you can do near field kind of experiments where you probe a mechanical oscillator external to a cavity and make very sensitive position measurements that way. Okay, so how do you make displacement measurements? So let's first remind ourselves very briefly that if you have a mechanical oscillator and it's in contact with the environment, then what you certainly have is thermal fluctuations. Okay, that's just given by the fluctuation dissipation theorem. And what this tells you is that if you have a system that has damping gamma m, then there is a fluctuating force that's proportional to kVt times gamma m times the mass. Okay, and that fluctuating force will make sure that the mechanical oscillator is in thermal equilibrium. And so what it means is the following: if you start to increase the damping of the mechanical oscillator, okay, so will the fluctuational force increase. Okay, if you decrease the damping, then also the fluctuational force will decrease. So if you want to make a very sensitive experiment, what you'd like to do is use a very, very high key resonator to reduce that fluctuational force white noise spectrum. So you can measure these thermal Brownian motion. So when we think about Brownian motion, then we mostly think about a particle on a microscope that it has some random motion. Well, clearly here, the random motion is more subtle because this is a mechanical mode with a well-defined frequency. So where is the Brownian motion taking place? Well, the Brownian motion, okay, takes place kind of in the phase space composed of the amplitude of the mechanical oscillator around its resonant frequency and the phase fluctuations. Okay, that's the kind of the two variables. So how can you measure observe this Brownian motion? Well, you send light into the resonator. You generate sidebands, Stokes and anti-Stokes. So these are is the phase modulation imprinted by the motion. And how would you measure these phase fluctuations? Obviously, you can't just put here a photodiode because you can't measure phase fluctuations with a photodiode. You need to have what we call a Hamiltonian detector. So what you do is you superimpose the output field with a local oscillator field. Okay, so you have a local oscillator field derived from the same input laser. Okay, you do balanced detection, so you have two detectors here, you subtract their photocurrents. So the only reason you do balanced detection is to get rid of any classical noise on a local oscillator. So for those that do balanced detection, that's one of the advantages. Yeah? So any input fluctuations on the LO are cancelled out in a balanced scheme. And your photocurrent, in the end, is just proportional to the phase fluctuation delta phi. So that's how you can do an interferometric position measurement. And well, how sensitive are you? A typical way to characterize this is using what we call the imprecision. So the imprecision gives you the noise floor in the levels of quanta. So if you have a noise, so a noise floor, an imprecision of 1 means that you can resolve the 0-point motion, or the motion equivalent to 1 quanta with a signal to noise of 1. Okay, so the ratio here of Sx to the motion created by the 1 quanta, which is twice the vacuum fluctuation, that's equal to 1. Okay, it's more technical, but I want to mention that. Yeah.
But this, for example, when you do this balanced detection, then there is a requirement of the synchronizations of the lasers. You use the same laser for beacon and for. Yeah,
and actually it's actually very subtle. So so in fact, what you have to do is you derive from the same laser. Yeah. But what's very important actually is that these two paths are balanced. And if you don't balance the paths correctly, what happens is that the noise, what you want to do is that the noise that arrives at your detector is correlated to cancel. So if you have now path length that is imbalanced, what will happen is that the noise in the difframeter will not cancel. So what you see is you start to see the classical noise, phase noise in particular, actually off the laser appear on your balanced homodyne. And but what is good is, and there's a very simple way kind of to calculate how well you can need to balance. If you want to detect the motion of a 1 megahertz mechanical oscillator, you can convert that 1 megahertz frequency into a corresponding length, effective path length. Okay, and you want to be synchronized to much shorter than that path length, say by a factor of 10. But for a megahertz oscillator, that's a kind of a vacuum wavelength of many meters, so you don't have to worry for low frequencies. At high frequencies, balancing becomes very important.
But also the detector, that it needs to be shot noise limited.
Yeah, so I'll talk about that. So what you have to do is, what's important actually, what you do in a balanced scheme here, so there's two things. First is you use a local oscillator that's much larger in an amplitude than a signal you're trying to detect. That's the first aspect. And why do you do that? Because then the beating of the signal with the local oscillator generates a photocurrent spectral density that's larger than the thermal noise floor. And so, so for instance, if you use a Newport balanced detector that we can buy here on a trade show, then if I take a power here of 1 nanowatt, I would choose typically about like at least 1 milliwatt in a local oscillator. Now the balance scheme becomes quite tricky when you violate that condition. So when you have a signal that's as strong as your local oscillator, actually a lot of approximations break down, and one has to be quite cautious. But in general, yeah, when using LO, much larger than a signal power. Then you can beat the thermal noise floor of the detectors and make a shot noise limited measurement. Now you might ask yourself, okay, are these the only things I have to worry about? And I'll describe in these measurements, the powers are typically not what you have to worry about. The problem is more that it's very difficult to get lasers that are shot noise limited in amplitude and phase quadrature at say a power of 1 milliwatt. And I'll describe some of the problems that exist in lasers and what lasers one should choose for these experiments. So, so if you now do this balanced homodyne, take the current, you can just plot it on an oscilloscope. It'll be a trace that looks like this, and you can now wonder, okay, where's the Brownian motion? Well, the Brownian motion that is occurring now in the amplitude fluctuations here, and also the phase fluctuations. So the mechanical oscillator's phase actually is randomly evolving with time. Okay, and if you take this trace and Fourier transform it, okay, you get a mechanical spectrum. You see the eigenfrequency, the width is the damping rate, and if you integrate the spectrum, you get something proportional to kBt over 2. And so what a spectrum analyzer actually is doing, if you think about it mathematically, it's taking a gated Fourier transform. Yeah? So a spectrum analyzer, what it does is it calculates the autocorrelation function over a finite time, and that time is just the resolution bandwidth we choose. Yeah? Now another comment about these spectral densities, they are not always a very familiar unit. They're always expressed in the unit you want to measure, say meters squared, okay, per unit bandwidth per hertz. So, so in this case of displacement spectral density, it's meters squared per hertz. If we were to talk about amplitude phase noise of a laser, it would be hertz squared per hertz, so particularly non-intuitive unit, which is hertz again. If it was strain, it would be it would be just unit list divided by the unit bandwidth. So these are called spectral densities. Let me mention only briefly. So if you have this mechanical oscillator, you integrate the entire spectrum here. You get exactly equal partition. You get a thermal occupation, and you can derive from this the temperature of the mechanical oscillator. So in principle, you can use the noise spectrum to gauge what the temperature of the oscillator is. Now, just a quick comment: if the mechanical oscillator had more damping, okay, this curve would be wider, but the area would always be the same. Yeah. So if the mechanical oscillator Q was higher, okay, again, the curve would be sharper, but again, the area would be conserved. So the area is just what gives you temperature. Now, if you were to cool the oscillator, the entire area would change. So cooling would cause the area to be reduced and diminish. Now, a comment about noise. So we always hear, or often, quantum limited lasers. But the question you can ask yourself is, to what extent are lasers truly quantum limited? And so in quantum optics, what you learn is that the coherent state is the vacuum just displaced, right? And that's what you learn. And unfortunately, that's not the reality. So in any laser, what you typically have is the laser rate equations are nonlinear. You have relaxation oscillations, and there will be a frequency range where this is a very good approximation. That's in particular at high frequencies, so high fluctuational frequencies, much below the relaxation oscillation, above relaxation oscillation. But typically, if you go to lower frequencies, closer to the carrier, you'll have, typically a phase noise starting to dominate. So, so again, in the ideal laser, you would have a shot noise limited phase and amplitude quadrature that scales very simply. So the shot noise on the laser scales as P over H bar omega. And this already tells you something quite interesting. It's very easy to make a laser shot noise limited. Okay, all you do is you take a laser, even if it has classical noise, and all you do is you attenuate the laser till it's very, very weak. And when it's very, very weak and you have this P very small, okay, you will always end up having a quantum noise limited laser. You can make the classical noise always kind of disappear. Now, unfortunately, it doesn't work for the phase. For the phase, okay, the phase noise scales not with P, but rather with 1 over P. So in fact, no matter how much I reduce my laser power, the phase fluctuations will always be there. Yeah? So you can never get the phase fluctuations out of a laser just by attenuation. Opposite for the amplitude fluctuations. Classical amplitude fluctuations you can just attenuate until you're limited by the quantum noise. If you look at these two expressions and you multiply them, okay, there's a constant, and that's not a surprise because that's the Heisenberg uncertainty principle. Okay, yeah.
So you mentioned that your local oscillator is much stronger than the signal that you receive.
Yeah.
Then the question is, in the limit that your signal is
very weak.
Very
Yeah.
faint,
Yeah.
Would there be any merit from actually lowering locals?
Yeah, so that's a very good question. So you can ask yourself the following: where actually does the noise, if you do a balance detection, right, and you see in the end, say, a shot noise floor, where does the shot noise floor come from? You can ask yourself. And where it comes from is, it comes not from the fluctuations of the local oscillator, but it's the local oscillator beating with the vacuum noise of your signal. That's actually what gives you the noise, the noise floor. And that's why it's the noise in the signal that determines the noise floor in a homodyne and heterodyne measurement, and not the noise floor of the laser. So that's because any noise of the LO, in fact, in the end, it gets canceled out in this balance detection. And so it's really the vacuum noise of the signal that's relevant. And that's even with a very, very weak signal, any classical noise would show up in the LO, in the homodyne measurement, and would contaminate your measurement. And so that's just, like I said, I put here more review for those who want to look at it back later, just how we calculate the shot noise limited kind of values. Let me just make one remark. I mean, it is kind of amazing of how sensitive you can be and with optical lasers. So for instance, if you calculate the Rin noise, okay, of a laser, so this amplitude fluctuation divided by P squared, you evaluate this for 100 milliwatts, you get minus 175 dBc per hertz. And you will not find any laser that you can commercially buy that has that kind of noise performance. So a high power laser, okay, the shot noise limits will become extremely small, and you're typically always limited by classical noise. And so for the phase noise, okay, if you calculate kind of the phase noise, already 4 microwatt laser gives you, 0.5 hertz squared per hertz phase noise. So these are ridiculously small numbers, okay, that you get with tiny amounts of power already. So, so that tells you that typically when you operate with large laser powers, you will start to see kind of classical noises dominate.
But in many cases, when you want to estimate the optical phase, it doesn't matter if there is the noise if you do the optimal phase estimation.
What you have is you have to find device scheme to get rid of the classical noise. And so this is one. So in the balanced homodyne, for instance, the classical noise of local oscillator is cancelled because if you have balanced arms, the noise travels through both arms, and then in the photo detection process gets cancelled out. But but you have to. But now you have to be cautious. Just I'll describe in a second. If you do measurements where you can be sensitive to the phase amplitude noise. So for instance, if your shot noise or the classical noise drives the mechanical mirror and has a back action, then you start to worry about these noise levels. But let me just mention one more point. What causes actually this phase noise to distort? It's due to relaxation oscillations. Any laser has relaxation oscillations, okay, due to the nonlinear coupled mode equations of inversion and photon density. And these laser rate equations predict, for instance, for a diode laser that has a very fast kind of carrier dynamics, that these relaxation oscillations occur at gigahertz frequency. And that's precisely why these lasers are used in telecom. They're very frequency agile. But that also implies that at gigahertz frequency, they're not quantum limited. So there's an example here of a diode laser, and you can clearly see it as you're above the shot noise, even up to gigahertz frequencies in the phase quadrature. Now you can still be quantum limited in amplitude. All you take is a diode laser, attenuated to a few microwatts, and you will see shot noise. But the phase is not quantum limited for these diode lasers. Now, on the other hand, what you can do is you can use a gain medium that's slower. And this is, for instance, an example for a YAC or a fiber laser or tie sapphires. And you move this relaxation oscillation down to just a few hundred kilohertz, and then you generate lasers that are truly quantum noise limited. How can you verify? You look at a noise floor as a function of power and make sure that you get a square root of p scaling on a photodetector. Then you can verify that they're shot noise limited. And so that's actually why most of the sensitive experiments, including LIGO, are done actually with YAC lasers and not with diode lasers. So diode lasers are very good for communications if you want to very fast modulate, but certainly not good for very sensitive interferometric position measurements. And for instance, for delay line sensing, to really use fiber lasers. Now, just very briefly on this Brownian motion. So what you can do is you can also take the signal from the mechanical oscillator, decompose it into its sine and cosine quadrature, and then you can reconstruct this Brownian motion in phase space. And just again, for those, if you try to recover the Brownian motion picture, you have Brownian motion. Okay, but now, as I said, in the x1 and x2, in the quadratures of the mechanical motion. Okay. Okay, I wanted to speed up a little bit more and talk about other sources of noise. So this is a broadband displacement spectrum from one of these toroid resonators. You see many mechanical modes. Okay, this is array of breathing modes and many other modes that you have. The shot noise, it's increasing here. That's just the way we've plotted it, because we plot the shot noise as an equivalent displacement spectral density. Okay, and because there's a cavity filtering effect, if you do that, then in fact you have a rising shot noise here with omega squared. You see here that the shot noise is above the electronic noise, so that's good news. But if you look very cautiously, you wonder, okay, where's the difference come from between shot noise and the measurement here? So there's some more additional noise that you see starting to rise. And this is actually a very interesting noise source. So the noise source here that gives you, that is a difference between the theory and the experiment, that's a noise that's very ubiquitous in physics, and that's called mirror coating noise or thermorefractive noise. So if you take a body, okay, of a certain volume V, okay, and you ask what is the temperature fluctuation of that body, okay, and Landau-Lifshitz predicts that the temperature fluctuation is given by T squared divided here by the volume, density, and specific heat, and kV, K-Boltzmann T. So if you make a cavity very, very small, you get large temperature fluctuations. Yeah. Now, these temperature fluctuations can transduce into frequency fluctuations via the temperature-dependent refractive index, the NDT, or via the expansion coefficient, the alpha dt. So the smaller you make an optical cavity, the larger the fluctuations become. And this is called thermodynamical noise. Any kind of object has it. A macroscopic mirror will tend to have it less thermoreflective noise than one of these optical microresonators, simply on grounds that the volume is much smaller in the case of an optical resonator. So again, this shows you if you want to make very kind of stable lasers, for instance, it's a poor choice to use a small cavity. Because you have a small cavity, you make that volume very small, you make the temperature fluctuations large and also the frequency noise. And in the case of these microresonators, this is a quite sizable noise. It's easy to see. Yeah? And this limits kind of the measurement imprecision because you cannot distinguish anymore, okay, the motion of the mechanical oscillator compared to the noise floor. So you can also simulate these mechanical modes. Maybe one word about simulations. You can do this very simply, for instance, in COMSOL, or as I described, industry standard for FEM is actually not COMSOL, but called ANSYS. It's a fine element modeling software. What's interesting is you get very good agreement typically. So agreement is really much less than 1% if you know dimensions. And so these are very accurate at describing the mechanical modes of the structure. And you can run these on your PC just in a matter of kind of minutes. So you need to, the acoustic wavelength is large, right? So the digitalization in these examples here is typically not a concern. Okay. Now before taking here kind of the break that is prepared outside for us, I'd like to finish off in about 15-20 minutes, kind of the limits and sensitivity. So you can ask yourself how, precise can you measure the motion of a mirror that moves? And this leads to something called the standard quantum limit. I wanted to see who has heard of the standard quantum limit before in talks. Okay. So for those who attended last year, for instance, CLEO, Nurses Malvava gave a plenary, and she was also talking about LIGO, and there also there's a standard quantum limit. So there's a limit of how accurate you can measure position measurements of position, and they're just imposed by effect of quantum noise. And this was worked out first actually by Carton Case, but there's many other references where this was done. And so one very easy way to see how sensitive a measurement is the following. If you resolve the motion of a mechanical oscillator, okay, and what you can do is you can look at the peak spectral density to the background, okay, and as described, if you cool the oscillator all the way to the ground state, what would happen is you would take, say, n quanta initially, and you would reduce it by a factor of n, and then you would be at 1 quanta. So if your signal to noise is larger than the number of quanta in the oscillator, you know that you have in principle sufficient resolution to measure the equivalent of 1 quanta of noise. Yeah? So the signal to noise immediately tells you if that's the case. Okay, so if you want to describe now a quantum measurement, you need quantum noise. Okay, and the way this is introduced is by adding the amplitude quadrature and the phase quadrature. So this was also mentioned earlier as a question. So here is the equation for more time, not for the field A, but rather for the amplitude quadrature and the phase quadrature, which is just the sum and the difference of delta A and delta A dagger. So then you get the equations of motion that describe, for instance, how input phase noise, input amplitude noise, okay, gets transduced into the cavity and gets output coupled again. Now, if you do this calculation, what you find is, and I'll be more short here. So, okay, you need to know actually how the noise is correlated, and for vacuum noise, it's delta correlated. Yeah? So that's why you use in Fourier domain here. You have this delta function appearing. And another source often of confusion is that what you measure in a homodyne interferometer, okay, is the following. In the classical world, right, what you have is you have the electric field E, and you have the electric field E conjugate. So if you measure the intensity, right, what you measure is E times E conjugate, E squared, right? Now in quantum mechanics, it's more subtle because E is electric field. It becomes an operator now. E conjugate becomes E dagger, Hermitian conjugate, and the order of the two operators matters. Okay, so A dagger is not the same as A dagger A. So what you measure always is so-called symmetrized output spectral densities. So you have here Q dagger, Q, and it's symmetrized. But this is a small comment, and this, anti-commutator gives you here the vacuum noise 1. That's your shot noise. So quantum mechanics always enters whenever you evaluate operators at 2 different times, and whenever you evaluate operator products, because then actually it matters, okay, in which order something appears. A dagger is not the same as A dagger A. That's where you get the commutator. And this little 1 here is a shot noise, okay, and the term here, this is the noise the motion of the mechanical oscillator, and these are the transduction factors. There's a cavity cutoff that you see here. There's the photons in the cavity and the coupling rate G. And we call this our measurement imprecision. And if you look at this expression, then what it tells you is you can make that imprecision as small as you want by just increasing the number of photons in the cavity. If you make that larger, you'll immediately make that imprecision vanishingly small. Now, that's not the entire interaction. If you now what you can also do is you can ask yourself the question: what does the radiation pressure do to the mechanical oscillator? And what you can calculate, what I've shown on previous slides, is that as you start measuring more precisely, so increasing the number of photons in the cavity, there's a radiation pressure quantum back action. And this comes from the fact that there's quantum noise of the laser, okay, that leads to a radiation pressure quantum fluctuation that will drive the mechanical oscillator, and that will scale, in this case, with a squared. Okay, so you see here a squared, whereas in the sensitivity it was 1 over a squared, and so the product of the two actually is constant. Okay, so that's actually just a manifestation of the Heisenberg uncertainty principle. So what does it mean is, it means if you drive the mechanical oscillator stronger, so will you also, you'll start driving the mechanical oscillator due to these radiation pressure fluctuations. And if you now put everything together, what you see is the following. Your measurement has some noise floor, okay? That noise floor becomes lower the larger is the power that you subject to in your interferometer. At the same time, as you lower the noise floor, you will increase the back action. So the motion that you see here is composed of the thermal motion of the oscillator, but also of this back action. And this back action starts to increase with a squared, whereas the measurement noise floor decreases with a squared. Okay? And if you drive very, very strongly, what will happen is that the entire motion of the oscillator is just dominated by the measurement back action. And this you call the quantum back action dominate regime. And then you also have the thermal Langevin force that drives the oscillator as well. But that's constant. That doesn't depend, to good approximation on laser power. Now, if you look at these two equations, there's a trade-off, and there's an optimum point. There's a point whenever your measurement precision is in the measurement precision and the back action, the total noise that you have in your measurement, where that is minimized. And this is called the standard quantum limit. So let's take a look at kind of an intuitive interpretation of it. Imagine you make a measurement of a mechanical oscillator and you have very, very little back action, okay? So then what you start out with is the following. You have your little measurement signal that you can hardly see, okay, and your noise floor that dominates the measurement. In this case, you have too little imprecision. On the other hand, you can go to this back action dominate regime where you start, as shown here in this upper color here, you dominate the motion of the oscillator by the quantum back action. So it's very strongly driven by a measurement. The noise floor is very, very low. This is called the quantum back action dominant regime. And right in the middle, okay, is the optimum sweet spot. So it's a sweet spot where the background is made sufficiently low to resolve the thermomechanical motion, but at the same time, you're not dominating the motion of the oscillator by the quantum fluctuations. And at this point, actually, the total noise that your measurement adds is, in the ideal case, just half a quanta of imprecision. Okay, half a quanta of noise that you add, a quarter quanta from the imprecision, quarter from the back action. And this is called, in the community of gravitational wave detection, the standard quantum limit. Now, in these nano-optomechanical systems, you can very, very closely, with optical laser fields, approach that standard quantum limit. And you can also operate in this really quantum back action dominated regime. So, give you one example. What happens in this quantum back action dominated regime is precisely what I described. If you inject power in an optical interferometer, and this is an example of a membrane in an optical cavity here, what you see is that if, in the case of low power, the motion of the membrane is just dominated by Brownian motion due to its environment. But if you start to pump harder, what you see is that at some point there's not just the thermal noise of the oscillator, but also the quantum back action noise. And then the membrane starts to get heated. Okay? And this heating, okay, is the heating now not due to an absorption of photons, but rather to the quantum fluctuations driving the mechanical oscillator. And this has been here, this example, but it's work by Tom Purdue, observed on a membrane placed into a cavity that was operated at about 10 Kelvin of temperature to reduce the thermal noise. And then already with a few microwatt of power, you can see this radiation pressure quantum noise dominated regime. Now, what you can also do in the course of making such an experiment, you can make very sensitive measurements of position. So, this is an example of more of a historic survey plot showing kind of displacement sensing over the last decades. Okay, starting all the way with the first observation of Brownian motion. So there's really kind of micron scale kind of displacements. And if you look at what happened over the last kind of decades, then there's this kind of change of slope due to these optomechanical systems that are very precise in terms of their measurement ability and can operate in this region that where you start to be quantum back action dominated. Now, when you start to be so one interesting aspect about making measurements that are quantum back action dominated is the following: that while you're making a measurement, okay, the light that actually accesses the optical interferometer can get squeezed. Okay, and why is that? So if you send in a coherent state in the optical interferometer, what happens is that the amplitude quantum fluctuations will start to drive the mirror. So this is this quantum backaction noise. And what happens is this random fluctuations of the mirror now, okay, they change the cavity path length. So that means that you're correlating the amplitude quadrature with the phase quadrature of the light. Okay? And whenever you have a coupling of amplitude and phase, that will generate squeezing. That's the equivalent of a Kerr medium. Okay? So what happens in an optomechanical system is that if you drive on resonance and you drive sufficiently strong to make quantum backaction drive your mirror, and then the light that gets reflected will be squeezed. Okay, where is it squeezing? It sits somewhere between the amplitude and phase quadrature. Okay, that's where it sits. Okay, due to this coupling of the amplitude to the phase via the mechanical oscillator. And so you can see it directly in the equation. So the output, for instance, the output phase quadrature depends now, okay, on the input, amplitude noise that goes into the cavity. And if you, solve the equations, you can find the squeezing spectrum. And what you find is that in this case, that there is squeezing occurring. You can ask yourself, where does the squeezing occur? And the squeezing does not occur, okay, on mechanical resonance. And it's very clear why. Exactly on mechanical resonance, mechanical oscillator has many thermal quanta. Okay, but if you go away from mechanical resonance, what happens is there's a window appearing, okay, where you start to squeeze the light field. Okay, and the interesting aspect here is that if you go away from mechanical resonance, okay, the thermal noise decays with 1 over detuning squared. Okay, whereas the signatures of these quantum correlations due to squeezing, they are long range. They go with 1 over delta omega, and there's a window opening where you start squeezing. And there's been quite some impressive progress in squeezing. So in the field of optomechanics, there's now, I think the record is almost 2 dB of squeezing at moderate temperatures of a few 10 Kelvin. So it shows here a homodyne detector spectrum, where the yellow line is when you just block the input to the homodyne detector. You just see vacuum noise beating with your local oscillator. If you now take your hand out of the LO, what you would see is, of the signal beam, you would start to see that there's noise actually that gets below the vacuum fluctuation of the detector. So it's a very non-intuitive situation where you have suddenly noise dropping even though you're sending light, in the interferometer. And this actually is now an example of this ponderomotive squeezing. So it's just you generate squeezing by driving the oscillator with quantum fluctuations. So what I'd like to suggest to do is I think there should be, I think 8 minutes of kind of a break here and some coffee. So I'd like to just spend a little bit of time just explaining this optomechanical cooling and the cooling physics in such an optomechanical system before taking a break. And so, so let me go back to these very simple kind of equations. You have the mechanical oscillator coupled to the light field. And if you want to solve this set of equations, what you do is you just assume that you have an optical field. And you get Stokes and anti-Stokes sidebands. And these sidebands are just shifted up and low with respect to the carrier. And if this is your ansatz, then you can very simply immediately solve the equations of motion and find what the shifting damping rate is and the shift in the eigenfrequency of the mechanical oscillator. Now, so the first thing you can do is ask yourself is what happens if you, for instance, sit on left side of the resonance versus the right side of the resonance. Okay. Now, what these optomechanical equations of motion predict is that if you sit on the right side here, what happens is you get an optical spring effect that shifts your mechanical frequency, to lower values. So you have a spring softening. Whereas on the upper side here, the blue sideband, you would see actually a tightening, and shift to higher frequency. And these effects can be quite pronounced. So this is an example of a photonic crystal cavity, a beam cavity. What you can see here is that even though the mechanical eigenfrequency at low power here is about 15 megahertz, you can shift that frequency all the way to about 7 megahertz. So you have a gigantic kind of ability to spring shift, the eigenfrequency. And there's even examples where mirrors placed on pendulas that have a natural frequency of a few hertz, where they're always spring shifted to hundreds of kilohertz just by using the laser field. So you can have very, very strong optically induced rigidities. And those are occurring whenever you detune your laser, either on the right or left of the Lorentzian. So that's where kind of change in intercavity photon number with respect to the motion is the largest. You can also cool the oscillator. And a very simple way to understand why cooling and amplification that was introduced by Brzezinski occurs is the following. If you send light and bounce it off a mirror, you generate Stokes and anti-Stokes sidebands. Yeah? And these two sidebands if the mirror has very high temperature, okay, they're exactly the same. Okay. In fact, quantum mechanically, one would be scaling like n plus 1, one goes like n. But if temperature is very high, they're very good approximation, they're the same. Now, if you now place that oscillating mirror in front of a second mirror, that second mirror will create a density of states. And if you arrange the density of states in such a way to enhance the blue sideband and suppress the red sideband, you've created an imbalance. But this doesn't come without a cost. So if you generate an imbalance, you have more blue photons than red photons, that costs you energy. So where does the energy come from? So that energy actually comes from the mechanical oscillator. That energy comes actually from the mirror. So the fact that you have generate this imbalance with the cavity, okay, if you imply just or stipulate energy conservation, you can immediately calculate that you have a cooling rate. And that's actually energy removed from the mechanical oscillator. On the other hand, if you do the opposite, if you enhance the red sideband, suppress the blue sideband, okay, we have more photons with lower energy, less photons with high energy. So now we have released energy, and that energy is transferred, okay, to the mechanical oscillator. So in this case, okay, there's energy being deposited in the mechanical oscillator to compensate for the redshift of photons here. So and so if you want to do this calculation classically, this is exactly what you do. All you do is you just calculate what your Stokes anti-Stokes sidebands are in this cavity, and from that energy, from energy balance, you can come up with a cooling rate, and it's rigorously correct. That's quite similar to techniques also that are used have been proposed in atomic laser cooling. Actually, there's a paper by Stephen Chu, not far from here, on laser cooling of ions and molecules by coherent scattering. That's very similar to this Brzezinski scheme of sideband cooling. So if you think about nonlinear optics, you can also think about this optomechanical interaction as a kind of a Raman process. So if you have a photon, so amplification would be the scenario where you have an optical pump photon, you generate the redshift, the Stokes wave, and the phonon. So it's very similar to kind of a Brouillon process in optical fiber, whereas the reverse process of cooling is where you take a phonon and a photon to give you here this redshifted sideband. So now one of the comments I want to make is that which process occurs here depends in our optomechanical systems on the detuning, if you red or blue detuned. And a second important part is that these processes, okay, only can occur, okay, if the dissipation rates are very dissimilar. So in Brouillon scattering and optical fiber, okay, why do you have amplification? Why does a wave actually get amplified in Brouillon scattering and optical fiber? And the reason it gets exponentially amplified is that once you generate the phonon here, okay, that phonon decays very quickly. And that's actually important to coherently build up the Stokes wave. In optomechanics, okay, the roles are reversed. What you do is the cavity here, the cavity photon exits very quickly from the cavity. The phonon is actually long-lived. And that's why in a phonon laser, what you do is you amplify coherently the phonons and not the photons. Okay, but it's really important to have these very dissimilar damping rates in Brouillon scattering and also in optomechanics. So how does this effect look like? Okay, so if you take a laser and detune, okay, along one of these, for example, these microresonators, what you see is that the damping rate increases on the red sideband, so that's cooling, and it decreases on the blue sideband. And it's a region of parametric oscillations where the oscillator generates coherently. Now, if you go to this blue sideband here, red sideband here, where damping increases, there's something interesting. It's not just the damping is increasing, but you're really cooling. And you can immediately see that if you just look at the noise spectra. So you see the noise spectra here. So what happens is actually they're getting wider. It's maybe hard to see. But the key is that the area is reducing. And the fact that the area is reducing tells you that you're really effectively lowering the temperature of the mechanical oscillator. So this is cooling that's, you're just cooling 1 degree of freedom. And so for instance, the CLEO, there's also another technique that was featured many years that's called this bulk Raman cooling, where people make doped crystals and they use any-Stokes scattering to really reduce the temperature of a bulk crystal. And that's a technique that works effectively. Okay, you can even go down to 80 Kelvin. In that case, what happens is you're cooling the entire crystal. Here what you're doing is you're cooling just one collective mechanical mode. The rest of the structure still is at room temperature. So it's just one isolated degree of freedom that you cool. the entire structure is still at room temperature. You can also do the opposite. You can actually do the, maybe one more comment is that what happens in this cooling is that the thermal Lungerman source stays the same, but you add optical damping. And this doesn't come without a price, okay? Because whenever you have damping, there should also be a fluctuation dissipation theorem, okay? And so in the case of the mechanical oscillator, it means if that's coupled to a bath with some damping rates gamma m, then there's a fluctuation that enforces that you have equipartition. Now in the case of a laser field, there's dissipation, there's laser cooling, but there must also be a back action. There must also be some fluctuations. But these fluctuations actually are very tiny, okay? And you can ask yourself, why are they so small? And the reason they're small is that the laser field at room temperature, okay, because photons have an energy of 1 electron volt, right? And MKBT is 25 millielectron volts. It means actually that the mean occupation of an optical laser field at room temperature is very, very small. So effectively, this laser field acts like a reservoir with very low temperature. In fact, it's a zero temperature bath. And that's why you don't have to worry about the back action of the laser field itself. It gives them a finite occupancy. That's called the Quantum limit of laser cooling. And one can calculate that. And what you find is that whenever the line width of the cavity is very small compared to omega m, you can cool oscillators all the way down to their motional ground state. If, for instance, the line width of the cavity is very large compared to omega m, then you have the so-called Doppler limit. And that's actually one thing that's actually kind of interesting about these calculations. And that is, if you look at these kind of limits of laser cooling, then you say, oh, I've seen these expressions may appear familiar because these are exactly the same expressions as you have in also atomic laser cooling. In atomic laser cooling, this kappa would be the line width of the atomic transition. And if your atomic transition line width is very narrow compared to the trapping frequency, you would exactly get very similar kind of expressions. And the reason you get similar expressions is not surprising because these expressions are just manifestations of Heisenberg uncertainty principles. Because if you have an optical cavity and a photon escapes, it has a certain escape time. Yeah? And if you ask what's the energy uncertainty, okay, then what you know is that delta E times delta T, okay, must be equal to ideally h bar, right? And so what you can do is any uncertainty in the time gives you an uncertainty in energy. And that uncertainty in the energy is exactly this cooling limit. And that's why it's the same for atoms, ions, molecules, and mechanical oscillators. It's just a very fundamental principle. Now, how close can you cool mechanical oscillators? I mean, there's many works now that have cooled very close to the quantum ground state or even to the quantum ground state. So you can cool down to much less than the quanta. It suffices to say that at some point, all these linear interactions, they break down. If you pump a system very, very strongly, what you get is a so-called strong coupling, where the mechanical mode B here and the optical mode actually get strongly coupled, and then you get avoid mode crossings. And these avoid crossings, one has seen in many other fields, like in cavity QED, for instance. What happens actually here is a little more subtle. That the avoid crossing is not between the optical mode at optical frequencies and the mechanical mode, but rather what's happening is the optical fluctuations, okay, near frequency, near the mechanical mode will start to undergo kind of this avoid mode crossing. And then you get kind of these typical displacement spectra here where the mechanical mode splits in two branches, and also the optical cavity splits in two branches, and they're just coupled by the coherent coupling rates. So very, very similar kind of physics is also observed in these optomechanical systems. That's just the physics of strong coupling. Now what happens, however, if you do the opposite, if you start amplifying? Okay, so what happens, this is the last thing I want to do before the break, what happens if you promote the laser here, generate more red photons than green photons? So then you transfer energy to the mechanical oscillator. And so that means that your damping rate here will become negative. Okay? And whenever the damping rate compensates the intrinsic mechanical damping rate, you start to have a regenerative coherent oscillation. And so, so these devices behave just like lasers. Okay? And in fact, I should not say lasers, I should rather say maser. And why should I say that? That's the following. So first of all, if you pump, you would see that there's a definite threshold. Of a certain pump threshold, you start to get this oscillation of the mechanical motion. You have above threshold somewhere saturation. If you look at the power spectral density, you would see that the line width would start to get narrower and start to collapse above threshold. Okay? Now, and if you ask the question, what is the line width of such a coherent mechanical oscillation? then there's a very kind of nice and handy formula that's called the modified Towns line width limit. And it tells you the following. If delta nu naught is your intrinsic mechanical line width, then the line width of your above threshold laser or maser will just be the bare line width, okay, divided by the number of quanta in the oscillator. Yeah. So just as a historical remark, if you go down to Towns, the original paper, they don't express everything in quanta. That's why things look slightly different. But in the end, that's what it says. The more quanta you have in your laser field or in the phonon field, the lower the line width will become. Now, this factor here is weighted with 1/2 plus Nm. So what is this 1/2? That's just the quantum noise in the oscillator. And this Nm bar, that's just the mean thermal occupation. And now the analogy to a maser becomes very clear. In a laser, all you have is vacuum noise. That's a typical shallow Towns. This Nm is equal to 0. But in a maser, right, at room temperature, you would actually have a non-zero thermal occupancy. Yeah? And that non-zero thermal occupancy actually makes your line width larger. Okay? And so the line width of these optomechanical oscillators, they're fundamentally just limited here by this classical thermal noise. Another comment, many of you may be familiar with Brouillon lasers. So Brouillon lasers are a terrible form of laser. And the reason they're terrible is because a Brouillon laser uses the Brouillon gain. The Brouillon has 10 gigahertz frequency. At room temperature, you have about 30 quanta of noise. So you're already, to start with, you're a factor of 60 away from the shallow Towns line width limit of a normal laser. And so the same for these optomechanical oscillators. They're not necessarily very good oscillators for that reason, because even though they might have a beautifully high Q, okay, they come with thermal noise at room temperature. So that's why one has to be prudent about the use of these devices, of these parametric instability to make narrow line width oscillators. So that's kind of this comment I made here. Okay, that's the original formulation of the line width law, but you can write in this more kind of nicer form. It's more intuitive, and understand that this thermal occupation will limit your line width. Now, then the final slide before the break here. So as I described, actually, this parametric instability was originally formulated by Braginski in the 60s. And what's interesting is that in 2015, this was observed in actual LIGO. So this observation of parametric instability in advanced LIGO was carried out. This was not pendulum modes, but rather these were really bulk modes of the mirror. They were coupled to the radiation pressure field and start to oscillate. And so there's a limit, or pose a limit, to how much power you can put into LIGO. Okay, so I think with this, I think I would like to stop here for a break. Okay, so I'm still, I think, 2 slides or 3 slides from the last that I want to finish off from the first part that didn't go through. So, and one thing I want to mention is what you can also do with these very precise measurements of mechanical motion is you can do a technique called feedback cooling. And that's a technique that's actually very old. So feedback cooling actually is a technique. The idea is you don't use this radiation pressure back action to cool mirrors via this delay, but you just do a measurement-based feedback. So you measure the position, say, of an oscillator, and take that position information, okay? And what you do then is you delay it, or you can also filter it. And the effect of that filtering is that you turn the position record X into a position record X dot. So and that makes it. And then now, if you apply that to a laser as a modulation, you generate a force that is viscous, okay, and can cool an oscillator. And this technique has a name. It's called in particle physics. It's called stochastic cooling, and it was used to cool so-called betatron oscillations. So if you have a storage ring with protons, antiprotons, okay, those also have a kind of an axial kind of fluctuation. And in experiments, what was typically done in particle physics is you have a capacitor that measures the position of that beam, and you have a kicker that's across the storage ring, another capacitor, and that applies a force, and then cools the phase space and reduces the kind of the motion. And this measurement-based feedback, very controversial at the time in the 60s. People were thinking that you can't violate Liouville's theorem and somehow the phase space density is preserved That's not the case. In fact, you're doing work on the system, and the work, again, is sidebands. And these sidebands, again, you carry away energy, and that energy is removed from the oscillator. So that feedback cooling can also be applied to mechanical oscillators, and if you have very sensitive readout, you can cool very far. And so this is an example of such a feedback scheme. So what happens here, you have the thermal noise driving the mechanical oscillator, you have the back action noise and the measurement, and then this term here, okay, that's the measurement record, okay, plus the imprecision noise of your detector times the feedback susceptibility. And this feedback susceptibility, you can just, you just can control that by your feedback gain, and that will damp the oscillator. So this effect here is an effect of damping. And so you can rewrite the entire equation in such a way that you take your mechanical oscillator susceptibility, you add now to the damping rate this feedback damping term, and that will reduce the temperature of the oscillator. And now you're going to have a trade-off, because how far can you cool? Well, you can only cool as far as you can resolve the motion of your mechanical oscillator. At some point, you can't resolve any more the noise floor. And what happens here is the following. So you take your photocurrent, you feed it back on a second laser. In this case, we feedback cool a little kind of small string here. And what you see is that the area underneath the noise spectra reduces. And then something quite interesting happens is you start to dig here a spectral hole into your noise spectral density. And this is an effect that caused a lot of confusion in the 80s, because what happens here is you have a shot noise background, and your photocurrent spectral density is below the shot noise. So you may think, oh, I'm squeezing. I'm generating a current that's below the vacuum fluctuation of light. So what's really happening here? What's happening is the following. This yellow line here, that's the vacuum noise level of your detector. That's being detected. You feed that back into your feedback system, and you imprint this now, this vacuum fluctuation, as a classical modulation on the mechanical oscillator. Okay? And that actually starts to cancel that vacuum fluctuation. But in fact, what happens here in reality is that you actually are driving the motion of the mechanical oscillator. So you have a classical noise on the oscillator. There's nothing else than a replica of the vacuum noise at your detector. That's called squashing or in-loop squeezing. And this is, you can never use that to your metrological advantage. So lowest occupancy you can attain is exactly when you are, when you can't discern anymore the signal from the noise floor. And you can cool very far. You can, for instance, with feedback cooling, you can cool all the way to just a handful of phonons. There's an example of 5 phonons, okay, in such a near-field coupled system. There's now even papers in the field that are cooling even lower to 0.2 just by measurement-based feedback. And it's important for these feedback schemes that to kind of make sure that you don't lose any photons, that you are very efficiently coupled to the detector. This is also, in reality, truly a quantum feedback. Why quantum feedback? Because the feedback not only suppresses the thermal noise of the oscillator, but also the measurement-based noise. So you make a very strong measurement, you drive in the oscillator with quantum noise. So it's actually, it's being heated, but then via the feedback loop, you're also cooling that noise. So you're removing thermal noise and the measurement back action noise as well. So in the second part, I'd like to kind of switch gears a little bit and talk about just classical effects before talking about some part, again, that are quantum mechanical. I'd like to talk about what happens if you have a mechanical oscillator, an optomechanical system with 2 laser fields. I'd like to talk about the effect of optomechanically induced transparency, and then talk about dissipation mechanical oscillators and also really applications of optomechanics. And so I start with the phenomena of optomechanically induced transparency, and this effect has an analogon in atomic physics, and that's the following. In atomic physics, if you have 2 common ground state coupled to one joint excited state, marked in 3 here, then the following can happen. If you were to probe this transition 1 to 3 with this green laser beam, okay, on resonance, you would start to see absorption. But if you dress that level with a second auxiliary field here, with this shown in red here, then what happens is this dressing caused by the second laser field causes the upper state here to split and the transition to become transparent. This is called EIT, and there's different ways to think about EIT. One is in terms of level dressing. Another intuitive way to think about EIT is that's an interference effect. It's an interference effect between electronic pathways of absorption. So, the electronic wave function can be, effectively interferes destructively in this upper state 3 in the presence of these common 2 drive fields. Now, a very similar effect can also exist in optomechanics. Here, what interferes are not electronic wave functions, but just optical fields. And so if you have, for instance, a strong control laser, and you have a weak little sideband that you inject into the cavity, you would normally expect this little sideband here to just follow the Lorentzian profile of the cavity. But it doesn't. And the reason it does not is the following, is that the moment this difference between the control field and this little sideband is exactly omega m, the mechanical frequency, you start to drive the mechanical oscillator. That driven mechanical oscillator will generate sidebands. One of the sidebands, the anti-Stokes, is strongly suppressed due to cavity density of states. The Stokes sideband is enhanced, okay, and it can interfere with the original field. And because an oscillator has a phase shift of 90 degrees on resonance, this interference is destructive. And so that causes now this little probe field to see the cavity Lorentzian, but right on resonance, where you have this two-photon condition of two-photon resonance met, you actually start to see an absorption dip and a transparency window open. And so this is now similar to EIT, but it's simply electromagnetic interference. This can be very narrow, this transparency feature. So this, first of all, it's tunable. So you can actually, by increasing the power on the lower sideband, you can make that transparency feature deeper and wider. And the width of that feature in the weak probe limit is just given by the mechanical damping rate. And so you can make this exceptionally kind of narrow. And I give actually details here on the calculation on the slides. So you can see it here. So as you increase the power, this dip becomes deeper and becomes also wider. And the width of this dip here is just given by the damped mechanical oscillator, because you have a strong field on the lower sideband that damps the mechanical oscillator, then a beating with the red sideband drives it. So what you see effectively here is the damped mechanical oscillator response. Now, what can you use this effect for? Well, there's a number of actually applications that have been conceived. So the first is you can slow and advance light. Obviously, if you have a very narrow amplitude response, you also have a correspondingly narrow phase response. And whenever the phase changes with frequency, you get a group delay. So d phi d omega is a group delay. So if you send in a narrowband pulse, it will get delayed. Now, what kind of delay can you obtain? Well, fundamentally, you can never delay a pulse more, okay, effectively the inverse bandwidth. So that's the, you have a delay bandwidth product that's finite for Lorentzian resonance. But there's an application where this becomes actually quite interesting. And this application has to do with LIGO. Because what LIGO needs to do is they need to rotate the quadrature of optical fields. And as LIGO detects in low frequencies, 0 to 100 hertz, they need to change the quadrature of a frequency from 0 to 100 hertz. So they would need to have a cavity with a 100 hertz line width. And one way you can do this quadrature rotation is actually using this optomechanically induced transparency. So if you inject light, okay, because of this change of the phase with respect to frequency, the light that is emitted from the cavity actually has a rotated quadrature, and it can rotate over a bandwidth here that's given by gamma m. So this is one of the applications now that's been conceived for this optomechanically induced transparency to be used for. So for kind of, yeah, quadrature rotation of light that is used for gravitational wave detectors. You can also use to amplify signals. For instance, if you take this OMET, but place the pump not on the lower sideband, but upper sideband, you can generate an amplification process. And you can amplify light or mechanical motion for that purpose. Is this the low noise amplifier? Well, if the mechanical oscillator is in a high temperature, you will actually just, the noise figure is just dominated by the residual thermal occupancy. So it's not necessarily very low noise. What's more interesting is you can use this if you can cascade this OMET effect. So if you have first resonance, here you have a second resonance, and you have two pumps on the lower sideband, then what you would expect is for a single mode is that when you inject your tone, that you see this transparency window open. But what's rather non-intuitive is if you have two of these OMET windows, and you inject actually a small little probe in the first, it appears in the second resonance, or vice versa. So you can do frequency conversion this way. And if, for instance, one of these resonances is a microwave resonance, one is an optical, you can do optical to microwave conversion. I'll show actually this application at the end. So let me turn to another kind of question one more time, and this is this question of these sidebands. And yes?
So for the EIT, like in the atomic case, like the Gaussian around this like narrow Lorentzian is coming from like whatever broad mechanism.
Yeah, exactly. Yeah.
So mechanical cavity, like what's this broad thing?
Yeah, so it's just so the fundamentally kind of it's just energy relaxation. So there's typically in optomechanical systems. I mean, you don't have to worry so much about dephasing mechanisms because those occur at a very, very slow time scale. So it's mostly just purely kind of, your T2 is just 2 times T1, your energy relaxation. And then the width of that window is just given by how much damping you apply to the lower sideband here. So the stronger you pump, the wider this transparency window becomes. because of the damping rate you induce. So that clarifies, yeah.
Right. The phase response plot on the screen looks like the phase jump. Is that achievable like by tuning the wave? So when you have like micro cavity and then the
Yeah, this is just a phase response that is associated with this type of amplitude response. So it's just Kramer's Kroning relating the two. And so you could measure this simply by, sending light, by making a phase sensitive measurement. Okay, so if you had an IQ detector, for instance, an optical one, you could actually find out actually what the phase response is. Typically, you would, if you just have an amplitude detector, then obviously this is what you would measure.
In the previous case, like
Yeah.
like you have a broad kind of like band and like you have a narrow dip. The narrow dip is coming from the.
So this is when you apply. So when you have what's varied here is actually the probe power. So the power here in this sideband in a bar. So as you increase the power in this lower sideband, you keep the probe always constant here. What you see is that you start damping the oscillator. That's actually why it gets wider, but also the dip gets deeper. So it actually scales with transmission scales as C over C plus 1, where C is the cooperativity.
The larger thing that goes up in the top figure, like not the deep, but the.
Yeah, that's actually in this case this is the intracavity field. So and typically what happens if you were to plot transmission, what happens actually transmission initially is actually the minimum at 0, and actually then it would go up all the way up to 1 in the strong pump case. So here actually what's plotted is the intracavity field. So the intracavity field is kind of decreasing, indicative that you have a larger kind of transmission past the cavity. So, so one thing I want to spend a little time on, also because it's related to some interesting quantum noise thermometry applications, is this question, okay, what happens if you send light, bounce it off a mirror, you get two sidebands, Stokes and anti-Stokes sidebands. And as I described these two sidebands quantum mechanically, okay, they are not the same, okay, and one will scale with n, one will scale with n plus 1. And where plus 1 is coming from depends actually on the detection method that you're using. So, so any harmonic oscillator that is, say, coupled to a bath, if you look at its noise spectral density, it will have this n plus 1. N is its mean thermal of quanta, and this plus 1 here is coming from the mechanical or quantum mechanical commutator of the mechanics. Yeah. And so at low temperature, what you would therefore expect is if you cool that mirror to a bath, at very low temperature, then you would actually see that the anti-Stokes sideband here, that would just, in this case, scale with n, so it would actually vanish, whereas the Stokes sideband scales with n plus 1, and that would still remain. And so from that asymmetry, you can measure temperature. And so this is precisely what is done in Raman noise thermometry. So if you look at the Stokes sidebands and any Stokes sideband scaling with n plus 1, by looking at the ratio, you can find out what the corresponding energy of the harmonic oscillator is and its corresponding temperature. And this is an effect that is very well known, in particular in atomic physics. So if you look, for instance, at some early examples, observation of quantized motion of rubidium atoms in optical lattice. So here, these are atoms that have in their lattice frequency about 100 kilohertz. If you look now at the Stokes anti-Stokes, you would see a very strong asymmetry indicative of a very, very low temperature. Now, these are atoms cooled to exceptionally low temperatures. This asymmetry is very naturally present if you look at crystals. So crystals have phonons, and if you look, for instance, at diamond, the phonons are 10 terahertz, roughly in that range. And so at room temperature, molecules are in their quantum ground state. And so that's why in Raman scattering, if you do Raman scattering of samples, here's an example of Raman scattering of silicon, the anti-Stokes and Stokes, okay, they're very asymmetric. And here's an example showing a temperature series, okay, from 400 to 700 Kelvin, and where you can see the variation of Stokes to anti-Stokes ratio due to temperature. So you can use this ratio as a kind of as a way to have an calibrated kind of thermometer, and there's no calibration needed. The calibration that you're doing here is just on the quantum noise. So the asymmetry gives you a quantum noise thermometer. There's no secondary calibration required. So just a quick comment. This is more for some experts. You can also ask yourself, okay, where actually do these asymmetries come from of a mechanical oscillator? And I think what I would like to show is kind of the following, that so these are really more details, but I want to get the main kind of idea out. So this Stokes anti-Stokes scattering, okay, where it comes from, depends kind of what measurement you're doing. Okay, so let's take an example. Okay, imagine this is your Stokes and anti-Stokes sidebands that you measure, and imagine you do detection with a photon counting module. So if you have a photon counting module, what it does is it destroys photons, right? So if you measure a Stokes or anti-Stokes photon, it turns out that the asymmetry just comes from the commutator of the mechanical mode. Yeah, and this is what you do in Raman scattering. But there's another way to detect Stokes and anti-Stokes sidebands. You could also decide to do a heterodyne measurement. Okay, so what you do is you take another local oscillator, and then you generate two beatings. Okay, the Stokes and anti-Stokes beating, okay, with a non-symmetrically placed local oscillator. Okay, and you can record those. And in those cases, it turns out that the symmetry of Stokes and anti-Stokes doesn't come from the mechanical oscillator's commutator. So it's vacuum noise, but it actually comes from the vacuum noise of your field, of your local oscillator. And so it's actually rather interesting. So it's just the way kind of quantum mechanics works out. But the result is in both cases the same. And the result is that n+1 will scale differently. And so if you're really interested in this, actually this is, in these references here, this is described. So you can see these asymmetries. This is one example in these feedback cooling experiments. So if you look at the asymmetry ratio as a function of the temperature of the oscillator, once you start to cool down to these 5 quanta, what you see is you see an asymmetry here of about 10%. That's not a whole lot, but it's exactly what you would expect for an oscillator of about 5 quanta of occupancy. And what happens if you go into the squashing regime, in fact, what happens when you go into a squashing regime, you lose that asymmetry again because actually you're driving the oscillator. You're driving the oscillator with noise of the detector, and then you start follow these blue bands here up of heating. So let me now talk in this last part. I'm going to switch gears, and what I'd like to talk about is two aspects. One is I'd like to spend some time about dissipation in mechanical oscillators. So where does energy relaxation come from? And also I'll talk about applications of optomechanics. And so those are two last parts, and they also weave into kind of modern kind of developments of the field as we've seen it in the last years. So dissipation. So what kind of dissipation mechanisms exist for mechanical oscillators? And there's some very obvious ones and ones actually which are quite subtle. And also there's mechanisms which are profoundly different from mechanisms that we know in optics. So the first very obvious ones is gas damping. Yeah. So if you have a mechanical oscillator, in an environment, then you can have, or in a gas, then obviously the impingement of molecules will actually cause viscous drag, and you generally distinguish between a molecular and a viscous regime, and you have to be at sufficiently low pressures to make sure you're not gas damping limited. Now, the more interesting one is the radiation loss. Yeah, so just like a dipole can radiate in free space, if you have a mechanical oscillator, it also will generate elastic waves. And so if you have a mechanical oscillator sitting in the middle here, what it does is, in a substrate, it will radiate elastic waves in the far field. And that's just the equivalent of radiation loss of an optical cavity. And then there's the last part, which is the material. And this has some rather interesting and intriguing phenomena, as it turns out, that relates to two-level systems. And so ultimately, if you remove gas damping and remove radiation damping, you're always left with the material quality factor. And the way you can obtain and remove this contribution from radiation is just by clever engineering of your mechanical oscillator. Yeah. And so one of these clever kind of ways to engineer is to do the following: is to, if you have, for instance, a mechanical oscillator in terms of a beam here, it will radiate into the far field. So this is just a non-mechanical beam on a silicon substrate. You see elastic waves going into the far field. This is a low frequency plot. This is a high frequency plot. What you can see is at a higher frequency, actually, you have more acoustic power that's being generated and radiated. And so how can you avoid a mechanical oscillator of radiating acoustic energy? And one very natural way is to use photonic band gaps, just the way you use them also in optics. And so what's shown here is a membrane with macroscopic dimensions, like centimeter by centimeter. And this membrane is patterned, okay, with these small masses and large masses in this two-dimensional array. And if you have a small mass and large mass, you generate a band gap. You open up a band gap. Yeah? And if you now place a localized mechanical mode in the middle here, precisely in that band gap, okay, it won't find any frequencies to radiate into. And one of the aspects where mechanics is profoundly different than in optics, as you know very well, it's very difficult to generate a 3D band gap, right? Because even if you have a, say, photonic crystal slab, it can still radiate in free space modes. But one of the nice things about mechanics is there's no such thing as a evanescent field for phonons. So if you have a patterned slab, it remains strictly two-dimensional. It cannot couple, okay, unless you had gas molecules around. It can't couple in a third dimension. So it's much easier to generate band gaps, true full band gaps for a mechanical system than for optics. And so in this case, for instance, if you place a mechanical mode in the center here, it will not radiate. And you can have a phononic shield, say, for a membrane oscillator. Now, so this is how it works. So this is a 2D example to kind of understand it. If you have a large mass and a small mass and then have a defect in the middle, then as I described, you will generate a band gap, okay, shown in gray here. And the size of the band gap just depends on the acoustic impedance mismatch between the large blocks and the small blocks. So the larger the mismatch is, the larger will this stop band be. And then if you place the defect frequency right in this band gap here, then the mode cannot decay. And this you can also see in the simulation. So if you place this defect mode right in the center of the band gap, what you see is a very localized mechanical mode. There's very little motion actually in the surrounding band gaps here. So you generated here a localized mode that can't radiate. And so the mechanical Q in that case would just be limited by the intrinsic material properties. Now, so one aspect that is very interesting is that you can also use this idea of phonon or mode shape engineering to reduce losses just by the geometry of the mechanical oscillator. And to understand how that works, I'd like to show an example here. And this is the physics of the quality factors of a suspended mirror. So if you have a mirror that simply sits on a suspension, on a fiber suspension, okay, so just this, a tensioned guitar string, okay, where the tension comes from a piece of a mirror here that sits in the gravitational field, you can ask what is the quality factor of this suspension, okay? And that was worked out originally by Salson in the context of these gravitation wave detectors. And it turns out that the quality factor Q of such a suspended test mass has a very interesting dependence. And the quality factor, okay, depends on the intrinsic material quality factor Q naught, okay? And then it scales like 1 plus the energy stored in the stress divided by the energy stored in the elastic elongation. And what this tells you is the following: if you make actually if you have a large energy that's in the stress, and that is larger, significantly larger than the energy you have in the elastic deformation, then the quality factor of the entire structure, okay, will actually be enhanced. And this effect is called loss dilution. And it has a very intuitive kind of understanding. And the intuitive understanding is the following. Imagine you have a mass, M here, and this is the mechanical oscillator with length L. And you're looking at the guitar string here. So mode, say second order mode, where you have here this characteristic mode shape pattern here. Now, first of all, you might ask yourself, okay, how do you introduce kind of damping in such a system? The way you introduce damping is the following. What you say is that the spring constant K, okay, has an imaginary part. Okay, that's called the loss tangent. That's typically how you introduce damping in a mechanical oscillator. So the relation between stress and strain, okay, is not exactly 90 degrees out of phase, but there's a slight phase lag. Now, if you look at this mechanical oscillator, okay, and ask now where does damping come from, okay, then a portion of the damping will simply come from the fact that the string here bends. Whenever it's bending, okay, you're making use of the elastic relation between stress and strain, and you're picking up from the bending contribution a loss due to the imaginary part of the spring constant. Now, at the same time, as this string bends, okay, it will also change, okay, the length, okay, L of the support here, and thereby increase or decrease the position of the test mass. Now, if you move a test mass in a gravitational field up and down, that's a conservative potential, right? You don't incur any energy, right? So moving, so a change in the length of the string here will change the mass position, and that will not lead to a loss. So bending via the loss tangent of the spring constant will lead to a loss. A change in the position of the test mass is lossless. And that's exactly behind that formula here. Okay? So the larger is the energy in the gravitational field. So U stress is really UG, U gravitational. And the larger that is compared to the energy you have due to the deformation, to the bending, the higher the quality factor of your mechanical oscillator will be. And this is called loss dilution, and it does not have an equivalent in optics. In optics, if you have an intrinsic quality factor of the material, there's no way you can dilute this loss. But in case of mechanical oscillators, for these flexural modes, these violent modes here, here's this very interesting property that the larger this test mass M is, the larger the quality factor will become, okay, by virtue of having a larger energy in the gravitational field here of this test mass versus the elastic energy from the bending. So that's called loss dilution. And if you then calculate rigorously what is the energy to the stress, what is the energy to the elastic bending, then what you find out is that the elastic energy scales with 1 over L squared, the stress 1 over L. And if you put both things together, you get a very interesting kind of relation, which tells you that you have an oscillator of a certain length L and a certain height or width H. Okay, then the ratio of this enhancement, okay, can be quite appreciable. Okay, the first term scales with H over L. The second term scales with H over L squared. Okay, so typically you're limited by the first term here, which is the smaller one of them. And that can be actually quite large. For this case, these fiber suspensions, that's about a factor of 1,000. So you can also see this effect. So here is an example of a strained string, so a string that's put under tension. And you look at the fundamental mechanical oscillator frequencies, and what you find is that the quality factor, actually for the fundamental modes, can be very high. So in this case, it's about 1 million. If you go to very high order modes, the quality factor starts to decrease. Okay, why does it start to decrease? Because this stress dilution effect actually starts to diminish at higher frequency. So it scales with this parameter lambda, which is H over L. And then you have M squared here. This is the mode order. For membrane, there's 2 mode orders, M and N. And so for this string here, if you go to very high order modes, say the 20 to 30 is overtone, then you just have the intrinsic quality factor. But at low frequency, the quality factor is actually higher than the intrinsic material quality factor. And it's that's actually very counterintuitive, because the Q here of the, so if you take a piece of silicon nitride, for instance, or glass, and you do an acoustic propagation experiment, you would find a certain damping rate. But now if you compare that damping rate to the violent mode here, you would find that that damping rate actually is here is much, much smaller. And this is a purely geometrical effect due to having strain. So if you add strain to the system, okay, for these flexural modes, you have this relationship that you can dilute the loss by the ratio of elastic energy versus energy in the stress. Yeah? But this effect only holds true for flexural modes, okay, for this violent type of modes, not for the bulk. So if you put the bulk on the tension and you launch an acoustic wave, that would be just propagate exactly with the intrinsic quality factor of the material, Q naught. But if you now have an elastic wave, okay, in terms of violent mode, okay, where you have a portion of energy in strain, a portion of energy in elastic deformation, then you can benefit from this stress dilution effect. Okay, and it gives you, as I said, this quite significant enhancements by about 3 orders of magnitude. Now, if you look at the expression more carefully, what you see is that there's 2 parameters here. So the quality factor scales as 1 over a term that goes like 2 lambda, and one goes like lambda squared. And this term with 2 lambda, this is called the clamping loss. So it's the actual contribution from where your mechanical oscillator is, clamped to the environment. And this term lambda squared here, this is due to the curvature of the mechanical oscillator. So going back to our picture, okay, the clamping contribution, the 2 lambda term is here and here, okay, and then the curvature here and here, that gives you the lambda squared term. So one is the clamping contribution, one is the antinode here. So what you can do is, there's a recently, about last 2 years, there's been very interesting new kind of approaches to increase the quality factor of mechanical systems further, and it is to engineer this kind of loss dilution further. And this is a concept called soft clamping. And the idea is the following. If you go back to this equation here, okay, of loss dilution, there's a term that goes like 2 lambda and a term that goes a lambda squared. And what you have to understand is that this lambda parameter is very small. Okay? So in fact, if you're limited by this clamping contribution, 2 lambda, okay, then this lambda squared term here is negligible. So what you can do is by playing with the mode shape, you can eliminate the 2 lambda dependence and only be limited by this curvature term here, which goes like lambda squared. And lambda squared, of course, is a much more rapid variation with h over L than the original lambda term. So thereby you can actually obtain significantly larger factors of dilution, which are here limited just by this clamping term. And so how does this technique work? So what you do is you take your localized mechanical oscillator and soft clamp it. And soft clamping means that you engineer the envelope of the mechanical mode and make sure that this decays very, very gently and softly towards the boundary. And so instead of having a very tightly localized mechanical mode, you have a very lowly localized mode. So it's a very shallow kind of defect here. So you have a very long-range envelope here. This eliminates this first clamping term. You're left with this antinode contribution. And this antinode contribution here has now this advantage that it scales with length over height squared rather than length over height. And with this, you can actually improve then by a significant amount your quality factor. And so for these 1D strings, for instance, here, you can see that if you use this soft clamping contribution, you can boost your quality factor by another factor of 10, okay, and thereby get, for instance, Q factors as high as like 100 million, okay, at megahertz frequencies. And so these are now QF products that are 10 to the 15, and the best values right now are even another order of magnitude larger. They're about 10 to the 9. So we have a QF of 10 to the 9. And so these are, like I said, exceptionally high kind of mechanical quality factors, but what one should realize is that the material quality factor, okay, is very low. So for instance, for silicon nitride, it's just a few thousand. And what makes you obtain these very large quality factors of millions is simply the fact that you're applying stress to the material and then use this soft clamping to eliminate the contributions from the clamping points. Now, where does these intrinsic material properties come from? So there's 2 contributions. The first is any mechanical oscillator has Zener loss. So if you have a mechanical oscillator that is undergoing deformation, okay, that deformation will generate locally heat. Okay, and if the deformation is occurring in a very slow time scale, that heat is in the end diffusing and causes a loss of energy. And this so this Zener damping is typically a damping that you have to worry about for low frequency oscillators at room temperature. Another loss mechanism, as I described, is just this clamping losses. And there's a very kind of beautiful experiment that shows how you can engineer them in another way other than soft clamping. So if you, for instance, take a membrane, you look at a fundamental mechanical mode, then this membrane mode will radiate into the far field, which in this case is a silicon substrate. Now, if you take, for instance, the second order mode here, so the 1-1 mode, it has a positive elongation to one side, negative elongation to the other. So if you look at how the far field looks like, what you have is you have elastic waves originating from either the positive or negatively oscillating hemisphere, or portion of the plate, and in the far field they will destructively interfere. And so if you look at different mode orders between even and odd, what you see is that the quality factor oscillates. And the reason it oscillates simply is that if you have odd modes, you have destructive interference of elastic wave in the far field. Okay, whereas if you have even modes, okay, there will be no interference. And so this you can see actually by this variation of the Q factor as a function of mode order. And so if you go, for instance, these very high order modes here, for 1, for instance, then you get a very nice destructive interference of elastic waves in the far field. Now, this only works, however, if the speed of sound in the material that you're coupling is much faster than the speed of sound in a mechanical oscillator, right? Because then actually the free space wavelength in your substrate becomes much longer than your device dimension. Then this interference actually can take place in a very efficient way. So that's another way, kind of, how you can engineer kind of the losses, not by using a photonic crystal, but rather by using just modes of proper parity that exploit this far-field interference. And so there's also a nice analogy you can make. So for those, this morning there was some talk about bound states in a continuum, for instance. Okay, what are bound states in a continuum? They're exactly this idea. You have 2 modes that can both radiate, right? And they're and what you do is that these two modes radiate in such a way that they interfere destructively in the far field. And so this is a similar concept, except that in bound states for continuum, it would not be one mode, but rather two modes that are coupled and superimposed. Here, it's just one eigenmode of the system that has this property of destructively interfering. Now, finally, you can ask, what about acoustic properties of materials at low temperatures? And here is something rather interesting. No matter what material you take, if it's amorphous, it will follow the so-called universality class of amorphous materials. And this was a large research field back in the 80s and even earlier, where it was observed that if you take an amorphous material and cool it down to very low temperature, and you do an experiment on a specific heat, then the specific heat was larger than the specific heat predicted by theory. And the reason it was larger is that if you have an amorphous material, you can think of this amorphous material as being kind of the equivalent of a crystalline material, where now all the unit cell have disorder. Yeah? And what this implies is that if you now look, say, at SiO2, so this is, for instance, quartz in the crystalline form, and here this is kind of quartz glass, so the amorphous form, then at low temperature, all these SiO2 molecules in their respective network, they have many equilibrium kind of positions, okay? And the different conformations, okay, they differ by energies that are very, very low. So you have very low-lying energy excitations. And the model that was then brought forward to describe glass at low temperature was from Anderson and Varma. And the model is that you have two states that can be two conformations of the SiO2 molecule. These two states are separated by some potential barrier. And this potential barrier is modulated by a strain of sound. Yeah? And that means that any phonon that will travel through the medium, okay, what it will do is will modulate the barrier height, and then also it modulates the tunnel coupling between the two. And this leads to very universal kind of phenomena for a so-called tunnel plateau for materials, and leads to acoustic attenuation that is within an order of magnitude for nearly all kind of amorphous materials. So no matter what it is, if it's wood, glass, or some other material, as long as it's amorphous, you cool it down to about 10 Kelvin, it will all follow kind of this typical tunnel plateau. And then the only unknowns are the density of these two-level systems and their vacuum coupling rate, and then their tunnel splitting. So acoustic materials at low temperature will always be dissipative. Okay? They have very low mechanical Q. And the only reason you can make mechanical oscillators at low temperature, very high Q, is if you use stress. If you use this loss dilution that I explained. If you part a stress to a material, then you can dilute that kind of tunnel losses. To get high mechanical Q at low temperature, what you need is quartz materials. Materials that have crystalline order that do not have these low-lying energies due to these conformal changes. And so crystalline quartz is a very good material. Silicon is a very good material. Anything amorphous will at low temperature, unless it's under stress, will be very low quality factor. And so this again leads to this kind of two components. So you have this so-called tunnel plateau that is very, very universal and with an order of magnitude for a wide range of materials. And then if you go to lower temperatures, there's a region where you have so-called direct phonon absorption, which is a situation where all your two-level systems are in a ground state. When an acoustic wave comes, okay, it starts to saturate these two-level systems. And so what has been observed is that acoustic propagation losses, they're intensity dependent, okay, in acoustic materials, in amorphous materials, for that reason that you start saturating these two-level systems. So, and this, again, is this a plot, and there's actually something to be said about this. So this is this paper mentioned. This is a nice review on this low-temperature thermal conductivity and acoustic attenuation of amorphous solids. And in this paper, I said they measured a wide range of materials and found that the mechanical Q was all within an order of magnitude. Now, a couple of years later, there's another paper that came out by Papia, is saying stress and silicon nitride, they crack in the universality dissipation of glasses. And so what they did is an experiment where they measured the Q as a function of temperature. And so you see, for instance, silicon here. So this is inverse Q. Okay, so low values to high quality factor. And I see, for instance, that silicon starts to improve rapidly, typically with a T-cube dependence, and getting these very high Qs here at low temperature. Now, you do the same for SiO2. What you find is that the Q is between 1,000 and 10,000. This is exactly what these two-level systems predict. Now you do the same experiment and you take silicon nitride, and suddenly your Q at low temperature is again 10 million. But silicon nitride is amorphous, right? So where does this difference come from here between a few thousand for an amorphous piece of glass and 10 to the 7 for silicon nitride? That difference is exactly this stress dilution I mentioned earlier. So by applying strain to a material, you actually are diluting the losses. So the acoustic propagation loss is still a few thousand, but if you measure a flexural mode of a nitride string, the Q can be 10 million. And so this is kind of this crack in the universality curve. It's just simply that you're diluting the stress. So nothing is kind of not understood here. It's simply that, yeah, you have to take into account loss dilution. Okay, so in the last part, I'd like to talk about what can you do with this optomechanical coupling? What are kind of possible applications? So why could this be possibly interesting also for technologies? And so of course some technologies that immediately come into mind that use mechanical oscillators as a medium of making measurements are, for instance, atomic force microscopes, AFMs, where you have, for instance, a magnetic tip on a cantilever. You generate a force via the magnetic interaction here. That force gets transduced into a displacement, and this you can read out optically. And you can do this in a very, very serious manner, as shown by Dan Rugar, where they have done kind of spin detection experiments to reconstruct, for instance, the form or the distribution of spins in a virus or in a protein, and do kind of nanoscale magnetic force resonant microscopy, MRFM. You can also make now a version of an AFM that's actually worked from NIST, where Karthik Srinivasan made an AFM cantilever read out optically. And the advantage here is that the optical cavity gives you kind of a higher kind of bandwidth of readout. But ultimately, you're always limited just by the thermal noise of your mechanical oscillator, so just by your gamma M, by your damping. Now, a very nice kind of application of optomechanics can be in thermometry. And so this is an experiment. So this plot here is this SQL curve I showed earlier. So if you are injecting low power, you are dominated just by the measurement in precision. If you increase power, your measurement precision reduces, and at some point, your quantum back action dominated. Now, if you do measurements in this regime where you're not limited by the quantum back action, then what it means is that your mechanical oscillator is just coupled to the thermal bath, and the quantum noise is driving very, the quantum noise fluctuations are negligible, and you're seeing just mostly the temperature of the environment. And if you now record Stokes and anti-Stokes sideband separately, you can measure temperature, okay? And in fact, in its measurements here, the temperature of the cryostat was varied between 10 Kelvin and room temperature, and even at room temperature, okay, that could derive the temperature via the Stokes and anti-Stokes sideband to a very high degree of freedom, very high accuracy within a few percent. So this can be a form of thermometer that goes all the way from 10 Kelvin to room temperature, where all you do is you record the motion of an optomechanical photonic crystal. So there's a mechanical mode at 5 gigahertz. You detect here in this case not the Stokes and anti-Stokes sidebands. What you do in this case actually you measure quadratures, phase and amplitude, and you can construct from this again the two sidebands. You look at anti-Stokes and Stokes, look at the ratio, and that gives you here the cotangents of h bar omega over 2 kBt. So you can pull out the temperature from this. Now you might argue, say this is a rather futuristic application. Can you really measure temperature with Stokes and anti-Stokes sidebands? And it's actually rather interesting to look into what technology already exists. And so this is a technology actually for my home country. So I live in Switzerland, and we have a lot of tunnels. And unfortunately, every summer, there's some accidents that happen in tunnels. And we have some of the longest tunnels in the world, the Gotthard-based tunnel, for instance, 80 kilometers of length. And so you want to know where an accident happens. And how do you do that? What you do is you do distributed temperature sensing. And in this application of distributed temperature sensing, you use this quantum mechanical commutator, this N+1. And the way it's done here is the following. You send a laser pulse through an optical fiber, and the mechanical oscillator here is just the SR2 molecules that have a vibration, and that is high frequency, typically terahertz, tens of terahertz of frequency. So there's a very low thermal occupancy at room temperature, okay, and will rise as you go to, say, 1,000 degrees or 2,000 degrees. And what you do is you measure the backscattered light, Stokes and any-Stokes, but you do that time resolved with a femtosecond laser or short laser pulse. And this is exactly what this Raman of OFDR are. So these are kind of distributed temperature sensing systems, and they do time of flight. And you have here then 2 gratings, get Stokes and any-Stokes, look at the ratio, do it time resolved, and then you have the entire temperature distribution along your fiber. And so in these applications here, of course, the scattering cross sections are tiny. Yeah? And with these nano-optomechanical systems, you generate many more photons actually per second than in this application. But it shows you that these are realistic kind of applications, and they are being used. This here being terahertz phonons, this here being phonons at 5 gigahertz. But the principle is the same. So that's actually one application I think where optomechanics is conceivable as thermometers that are quantum noise calibrated and that don't require any secondary calibration. Another example where, of course, mechanical oscillators are used, and this, of course, is a very, very large kind of market, is in accelerometers. And so the principle of an accelerometer is very simple. You have a test mass. That test mass undergoes thermal Brownian motions. At the same time, if you have an acceleration, you have m times a. That's your Newton's force acting on the oscillator, and you can if you have a large test mass, you can measure very small kind of displacements. Very small accelerations. And so, how can you measure the motion of a test mass? In your phones, for instance, you have about 5 to 6 kind of sensors for rotation, acceleration, and so these are kind of commodity products. They're sold already by the billions by companies like Bosch and others. They're typically monitored capacitively, so it's sufficient kind of to do a kind of motion sensing device. There's also piezo, another example. So strain goes into voltage. And also for high resolution applications, the optical interferometry is quite interesting. Okay, and I'll give one specific example. So what are the examples for MEMS sensors? So again, it's like a very, very large market. The sad news for optics is that there's very few applications where you need a sensitivity that optics can afford. So anything kind of relating to consumer products like cell phones, optical image stabilization, all this you can do wonderfully with capacitive readout. But there are some applications actually where it's quite interesting to have optical readout. And these are in particular kind of in the oil industry, in seismic applications, and also in applications of earthquake monitoring. And why is that? So what do you do in these applications? So for instance, in the case of if the oil industry, what they are doing is if oil fields are kind of becoming less kind of productive in the sense of being able to recover the oil that's in the different fields, what people do is, this particularly done in the North Sea, is you put a fiber optics sensor network in the ocean, and you detonate acoustic, or you detonate a little piece of explosive here and generate an acoustic wave. And those acoustic waves are traveling through different sediments. They're reflected back, and they're picked up. And they're picked up actually by typical kind of accelerometers. And depending on kind of the time and also the strength of the signal, you can completely reconstruct kind of the oil field and where the pockets of oil are. And so this is actually one application where you need very, very sensitive kind of accelerometers that are vastly more sensitive than the ones that you use kind of in your cell phone or in mobile applications. And so that's actually where optics becomes very competitive to existing technologies. So this is an example of an optomechanical accelerometer. So what is your ultimate sensitivity limited by? Well, it's simply the thermal noise divided by the mass. So it shows you again that you want to use a large test mass and have a very high Q mechanical oscillator. And if you look, for instance, at accelerometers, this is an example here from Oscar Painter's work from the past, then you can get acceleration sensitivity of nano-G per root hertz, and that's definitely competitive, or significantly better than commercial kind of accelerometers that I use. So this is one application where these optomechanical systems can do very well. Of course, the devil is in the details because in many cases what you want to sense is very low frequency. Yeah? And then of course you're back to the original problem that you have to worry about laser noise. Okay? So your thermal noise floor might be very low, but if the laser phase noise starts to increase close to carrier, then you start to lose that sensitivity. So that's why typical in these schemes, if you really don't want to do very well, you have to use a very kind of low Q cavity. Okay? Why low Q? You want to make sure that you don't transduce any phase noise of the laser into amplitude fluctuations. Yeah, as I mentioned, kind of the markets. So this is just a slide I took actually from our EU framework program. So as I said, you know, the markets, of course. So it's kind of interesting to see. So a really interesting kind of serious contender is energy, oil, and gas discovery monitoring. And there you need about, as I said, is nano-G per root hertz and also a very large dynamic range of 120 dB. And that's also something where optics can do very well. You can have very large dynamic readout. Other examples are, as I said, you know, these ground shape maps or earthquake detection intervention. But again, the two critical figures of merit here are dynamic range and then also the actual sensitivity limits. Another application, this is not so much in the consumer market, but still not uninteresting. It's also kind of contemporarily, you know, there's a lot of interest in this, is to utilize the fact that mechanical oscillators not only interact with laser fields, but also with, you know, with electrical fields. And so, for instance, if the same mechanical oscillator is coupled to an optical cavity and part of an LC circuit, what you can generate here are interfaces between light and microwaves. And in this case, for instance, what happens here is that the radiation pressure coupling couples an optical cavity field to a mechanical oscillator. Okay? And at the same time, this mechanical oscillator is formed part of an LC circuit, so it's a capacitor that's mechanically compliant, and so also it's coupled then to this LC circuit here in the microwave domain. And so what you have then is 3 degrees of freedom: microwave, mechanics, optical. And what you can generate here is the interface that converts, for instance, microwave photons all the way to optical photons or vice versa. And what's interesting here is that this interface can be completely bidirectional in principle. So you can convert bidirectionally photons from the microwave domain to the optical domain and back. Now, what's interesting about the scheme is that you can do this in a way that's very efficient and very low power. So if you think about, you know, how you do that in optics, you would take a phase modulator. A phase modulator, you know, takes an electrical signal and converts it to optical sidebands. Now, but a phase modulator, if you ask how efficient is it, can it convert, say, a single photon of a microwave field into a single photon of the optics? That's not the case. So the efficiencies are extremely low for typical commercial modulators that we use in telecom. So here, by using a high Q mechanical oscillator and strong optomechanical coupling, you can make this actually very efficient. And you can make these devices so efficient that, in principle, even a single microwave photon can be upconverted to a single optical photon and vice versa. And this is an example of such a device. So this is an example from NIST here with an optical cavity. There's a membrane that's sandwiched in this optical cavity and also in close contact with this capacitor network here. So this is the top plate, this is the bottom plate. They're sandwiched together. There's a little inductance here. And if you now inject a microwave photon and have an auxiliary microwave drive, then this microwave photon will appear as a sideband to the optical photon, and that can be extremely efficient. In fact, the efficiency here can approach kind of unity, and the noise that you add is simply the thermal noise of the mechanical oscillator. So you can make a very efficient kind of modulator. If you compare the V pi on this modulator with the V pi of a conventional one, it's about 6 orders of magnitude lower in value. But of course, it's a much narrower bandwidth. The bandwidth of which you convert, in this case, is just the mechanical damping rate. So it's a few kilohertz versus your gigahertz that you're used from a commercial lithium niobate modulator. Along those lines, another example here that's been demonstrated is you can use the same assembly without the optical cavity to make sensitive measurements of RF fields. So this is an example where you have again, L and a C. The C here is mechanically compliant. So it's in this case a membrane made from silicon nitride. And that LC just forms an antenna. It picks up radio waves. And what you do is you put on that LC circuit a constant voltage, so a static voltage. And if you apply a static voltage, you can get a strong coupling between a mechanical oscillator, okay, and the LC circuit. So they are, in this case, the LC and the mechanical oscillator both at the same resonant frequency. Now, what it means is that now, if you inject an optical signal into your LC circuit, because they're strongly coupled, half of the excitation lives in the mechanic, half of the excitation lives in the LC circuit. So they're shared. They're just shared eigenstates. And so what you can do now is, if you inject an RF tone, you can just read it off optically by reflecting light off the membrane. And now the fluctuations in the charges on your capacitors, they are now will be encoded into fluctuations in the optical field, which are nothing else than sidebands. And so you can make here a very sensitive transducer of RF fields to optical fields, okay, using just this interface. And if you compare this to state-of-the-art kind of amplifiers, we'll find out actually that this is very competitive. So this is as good as taking a commercial high mobility transistor amplifier and amplifying an RF field. And so the only noise that you add here is the thermal noise of your membrane. Yeah, again, this is the same scheme. This wavelength conversion I mentioned earlier, and this was mentioned for the RF the optical, and here it's just shown between two optical waves. So this, like I said, one application that is being pursued by a number of groups in the field. Finally, I'd like to also mention that a lot of the physics that I've described of these optomechanical systems not only pertains to optical cavities, but also can be studied in microwave cavities. So this is an example of a superconducting cavity that's made of aluminum. This is a vacuum gap capacitor. This is a spiral inductor. And this vacuum gap capacitor here is composed of two aluminum plates separated by about 50 nanometer. And there's a mechanical mode which corresponds to the vibration of the optical drum. And one of the applications or what you can observe here is this exact same physics. You can amplify, you can cool, you can read out. And one application, for instance, of such a vacuum gap capacitor is you can make amplifiers. You can make amplifiers for microwaves. And so if you have, for instance, two LC modes coupled to a joint kind of mechanical oscillator, you can actually make an amplifier for microwaves that using the mechanical oscillator as a gain medium. And in this application, what is interesting is that the noise that you add during the amplification process is the residual thermal occupancy of the oscillator. So if you cool that to the ground state, then you can make a phase-preserving amplifier, which just adds half a quanta of noise. So you can make low noise amplifiers using mechanical oscillators, not for optical fields, but for microwave fields. Now just one comment also about making non-classical states. So this optomechanical interaction can also be used to make non-classical states of mechanical oscillators, and this has been achieved actually over the last 2 years. There's been 2 papers by Max Assemeyer and Simon Groblacher. And the way this works is using kind of the optomechanical physics. And so imagine first you want to make a Fock state of a mechanical oscillator. How would you do that? So the way you could do this is you would first cool the mechanical oscillator on the lower sideband. So you remove all the thermal quanta, you cool to the ground state. What you do then is something non-intuitive. You place a pump on the upper sideband, and this will generate now a Stokes photon, okay, and a phonon. Okay, and if this upper sideband pump is very weak, okay, it will only occasionally generate a photon-phonon pair. And what you do next is you have a single photon detector. Whenever that photon detector clicks, you know exactly, okay, that you have generated the phonon. In fact, what you're doing is you're projecting a weak coherent state into in that moment you convert the weak coherent state, and this projects the mechanical oscillator into a Fock state. So this is called a projective measurement. And so with this scheme, for instance, you can generate Fock states of mechanical oscillators. And this has been recently demonstrated. So you can generate kind of the equivalent of the single photon state, but only in the mechanical domain using these so-called projective measurements. Now, could you use those for quantum metrology? Well, we are very far away from, I think, seeing something like this, but still it demonstrates kind of a very elemental control of mechanical systems, that you can also generate even complex, or in this case, simple kind of quantum states like Fock states. Now, finally, another comment is optomechanics, as it is described, is coupling light and mechanical motion. And you can also ask yourself, well, does optomechanics maybe also apply to other systems like molecules? And in fact, if you read literature a little bit, then you find interesting analogies. And there's one interesting observation that was made by Emery and Nee in the late 90s, What they observed is they looked at Raman scattering of gold particles that are mixed with molecules. And what they found out is that they could do stimulate Raman scattering experiments on single molecules. And that's very non-intuitive because normally single molecules will not scatter many photons, certainly not for Raman cross-sections, which are significantly smaller than typical cross-section for absorption. And what they found is that they stimulated these source experiments, so these are Raman scattering of gold surfaces, rough gold surfaces, leads to an amplification of about 10 to the 12. So enormous amplification of Raman cross-sections. And there's also been evidence for vibrational pumping. So that is to say, if you look at the incident power versus the Raman scattering, you see this superlinear kind of behavior. And what's actually interesting is you can also use optomechanics as a way to understand these experiments. Because what these are, you have a cavity in optomechanics. This is, in this case, your gold particles that are coupled. Here it's an optical mode. Here it's a plasmonic hotspot. You have a mechanical oscillator here. Here you have a vibrational mode. Of course, this vibrational mode is anharmonic, but if you have a large collection, it behaves harmonically. And what's quite interesting is actually that the conditions for back action are kind of very close to being satisfied. You have a plasmon has, say, a Q of, say, between 30, maybe, and say 30 or so, so a line width of 30, 40 nanometer. But these vibrational modes have frequencies of typically tens of terahertz. So if you do the calculation, you find actually that back action amplification is actually possible in such systems. So kind of this, and so you can understand also this source phenomena by just optomechanics. And there's another kind of way you can understand the experiment. So in the end, molecular optomechanics is probably already something that's been studied for many, many years. It simply wasn't described or understood per se as being a back action effect. Now, finally, there's a lot of reviews that appeared on optomechanics in last years, and I just put some reviews that I personally enjoyed, especially these issues here. And of course, I'm still around for questions. And I hope, with this that I could convey you some of the fundamentals of the field, but also tell you what people are excited in and interested in the last years, which is in particular the last part. And if you need questions, please don't hesitate to send me an email. So tobias.kippenberg@epfl.ch. I think it should be on the, I hope it was on the short course program. And I hope you have also an interesting conference here at CLEO.